What if the universe holds secrets so profound and bewildering that they could completely alter the way we perceive our existence? As scientists push the boundaries of our knowledge with cutting-edge telescopes venturing into the furthest corners of space, they are unearthing phenomena so strange, so mind-boggling that they challenge everything we thought we knew about the cosmos. One such enigma is dark matter and dark energy, two mysterious, invisible forces that seem to govern the very fabric of the universe. Though these forces shape the structure of galaxies, distort the path of light, and drive the expansion of space itself, their true nature remains an elusive riddle. Despite decades of research, scientists are still in the dark about what dark matter and dark energy really are. They play a role in nearly every cosmic event we observe, yet their properties remain one of the greatest unsolved mysteries in science. As astronomers delve deeper into the universe, their discoveries only seem to raise more questions than answers. This journey to understand the cosmos has brought to light not just the invisible forces shaping the universe, but also some of the most fascinating unsolved mysteries within it. One of these is the phenomenon of rogue planets. Rogue planets are among the most intriguing objects in the universe. These celestial wanderers drift aimlessly through space, unbound by any star, unlike the planets we are most familiar with, which orbit stars within stable solar systems. Rogue planets exist in isolation, their origins as varied as the stars they once may have been a part of, or perhaps never were. Some may have been born in the vicinity of a star, only to be ejected into the cold void of interstellar space due to gravitational disturbances or cosmic collisions. Others may have never been part of a solar system at all, having formed independently in the vast, starless reaches of the galaxy before eventually drifting into a star system, only to be ejected again. The characteristics of rogue planets are as diverse as their origins. Since they do not receive light or heat from a nearby star, they are typically much colder and darker than planets that orbit a star. Some of these rogue worlds may be composed mostly of gas, resembling the gas giants like Jupiter and Saturn. Others could be rocky or icy, with surfaces that are radically different from the ones we see on planets like Earth or Mars. But what truly sets rogue planets apart is the possibility that they might harbor atmospheres. While these atmospheres would not be warmed by sunlight, they could still exist thanks to internal heat, perhaps generated by the planet's core or from tidal forces as the planet moves through space. Detecting rogue planets is an enormous challenge, primarily because these planets do not emit light of their own. However, astronomers have developed a technique known as gravitational microlensing, where the gravity of a rogue planet bends and magnifies the light of distant stars, creating a temporary flash that signals the planet's presence. By observing these flashes, scientists can infer the existence of rogue planets and begin to understand more about their behavior. As technology improves, researchers are gaining a clearer picture of these elusive worlds, and early studies suggest that there may be billions of rogue planets scattered across our galaxy, each one contributing to the vast and complex tapestry of cosmic bodies. The very existence of rogue planets challenges our traditional understanding of planetary formation and stability. These nomadic worlds do not adhere to the neat, orderly structures that we typically associate with planetary systems. Instead, their wandering existence offers a glimpse into the chaotic nature of the universe, revealing that not all celestial dynamics follow predictable patterns. Rogue planets represent a wild card in the grand scheme of the cosmos, reminding us that the universe is a place of unpredictability, where the rules we have long assumed might not always apply. The discovery of rogue planets also opens the door to exploring new possibilities in the search for life beyond Earth. These planets may harbor unique environments, ones that are vastly different from the conditions on our planet. Could they host forms of life that are radically different from anything we know? As we continue to study these mysterious wanderers, we may uncover insights into the incredible diversity of planetary systems and ecosystems that could exist in the universe. Scientists are still piecing together the puzzle of rogue planet formation, and several competing theories attempt to explain how these cosmic drifters come into being. One popular hypothesis links rogue planets to the processes involved in the birth of star systems. When a star forms, it often gathers surrounding material, which can lead to the creation of planets. However, sometimes gravitational interactions, such as close encounters with other stars or objects, can disrupt the delicate balance, causing a planet to be ejected from its parent system. This theory suggests that rogue planets are simply the fallout from the dynamic, often chaotic events in young star clusters. Another theory proposes that rogue planets can form entirely in isolation, far from any star. In these cases, molecular clouds, dense regions of gas and dust that are scattered throughout the galaxy, can collapse under their own gravity. This collapse might lead to the formation of a planet without a star, as the gas and dust condense into a dense enough mass to form a planetary body. These planets would exist in the cold, dark regions of space, far from the warmth and light of any star, which might help explain the presence of geological activity on some rogue planets, despite their lack of solar energy. The concept of rogue planets changes our understanding of planetary systems and forces us to reconsider the fundamental assumptions about how planets, and the conditions necessary for life, can form and thrive. These rogue worlds are a testament to the infinite complexity and unpredictability of the universe. With every discovery, we inch closer to unraveling the mysteries that lie hidden in the farthest reaches of space, unlocking secrets that could forever change our understanding of existence itself. As technology advances and our ability to study these elusive objects improves, the rogue planet phenomenon will likely continue to captivate our imaginations and shape the future of space exploration. Throughout the cosmos, many theories attempt to explain the mysterious behavior of planets, particularly those that find themselves detached from the gravitational embrace of their parent stars. Some scientists suggest that such rogue planets, those that drift freely through the vast expanse of interstellar space, may have once belonged to solar systems, only to be violently ejected due to gravitational disruptions. These disturbances are often triggered by the complex gravitational ballet of nearby stars or the interactions of other massive celestial bodies. The resulting ejection of a planet from its orbit can be catastrophic, sending it hurtling through space, no longer bound to any star. These chaotic, often violent cosmic events underscore the unpredictable nature of the universe, where gravitational forces, acting like both creators and destroyers, play a fundamental role in shaping the very fabric of star systems. Each of these theories provides a unique glimpse into the turbulent nature of planetary formation, painting a diverse and evolving picture of how rogue planets emerge. Understanding how such worlds are born and how they navigate the vast emptiness of space expands our comprehension of planetary dynamics. It also raises profound questions. Could life ever arise on these solitary, wandering worlds, detached from the warmth of a star and adrift in the cold, endless void of space? Rogue planets, these enigmatic wanderers of the galaxy, have become a subject of intense interest and fascination. These celestial bodies, untethered from any star, have been detected with the help of cutting-edge technologies and innovative observational techniques. One of the primary methods used to detect rogue planets is gravitational microlensing, an effect that occurs when a planet passes in front of a distant star. The planet's gravitational field acts like a lens, bending the light from the background star and temporarily making it appear brighter. By analyzing these brief fluctuations in light, astronomers can infer the presence of the rogue planet and even estimate its mass. Another technique employed in the search for rogue planets is the transit method, commonly used to discover exoplanets orbiting stars. When a rogue planet crosses in front of a distant star, it causes a brief dip in the star's brightness. Telescopes equipped with highly sensitive light detectors can capture these tiny changes, revealing the presence of a planet that is no longer gravitationally bound to any star. Space-based observatories, such as the Kepler Space Telescope and the Transiting Exoplanet Survey satellite TESS, have proven invaluable in this quest. Positioned above Earth's atmosphere, these telescopes provide a clearer view of distant objects, allowing astronomers to detect faint light signals from faraway celestial bodies. Ground-based telescopes equipped with adaptive optics also contribute valuable data by compensating for the distortion caused by Earth's atmosphere. Furthermore, direct imaging has emerged as a powerful tool in the search for rogue planets. This technique involves specialized instruments such as coronagraphs or star shades, which block out the intense light from stars, enabling astronomers to spot the faint glow of planets that would otherwise be obscured. These advanced technologies improve our chances of identifying rogue planets, allowing scientists to better understand their composition, origin, and the processes that give rise to such solitary worlds. The ongoing exploration of rogue planets continues to deepen our understanding of planetary systems. These rogue worlds challenge conventional models of planet formation and stability, forcing scientists to reconsider the fundamental nature of planetary existence. Some rogue planets may have formed in regions lacking sufficient material to create stable solar systems, while others might have been expelled from their original systems due to gravitational interactions. Regardless of their origin, these solitary wanderers offer a unique perspective on the dynamic and ever-changing nature of our universe. Among the most intriguing rogue planets discovered are Kata T2, PSO J38 5338-22, 3992, and OGL 2016 BLG 1928. Kata T2, located around 30 million light-years away in the constellation Ursa Major, has a mass similar to that of Jupiter and is one of the first rogue planets to be observed at such a vast distance. Its position drifting through space without a parent star makes it a fascinating subject for scientific inquiry. PSO J318 533H22 3990, discovered in 2013, is another captivating example. Located approximately 85 light-years from Earth in the constellation Pictor, this planet is especially notable for its youth, approximately 20 million years old. It is considered a free-floating planet, having formed like a traditional planet but never having settled into an orbit around a star. This challenges our assumptions about how planets are formed and emphasizes the diversity of planetary pathways in the universe. Then, there is OGL 2016 BLG 1928, discovered using the technique of gravitational microlensing. Located about 22,000 light-years away, this planet is another remarkable example of how the universe's most elusive celestial bodies can be detected through innovative methods. The study of these rogue planets not only broadens our understanding of how planets can form and survive outside the gravitational influence of a star, but also sparks discussions about their potential habitability. Could life exist on these isolated worlds? How might these planets sustain themselves without the warmth and energy provided by a parent star? The study of rogue planets also intersects with another area of cosmic mystery: gravitational anomalies. These anomalies present a challenge to our current understanding of gravitational forces, often manifesting as unexpected variations in gravitational pull. Such discrepancies arise in regions where we would typically expect uniform gravitational behavior, such as near massive celestial bodies. These anomalies invite scientists to question whether our existing models, based largely on Newtonian gravity and Einstein's theory of general relativity, are sufficient to explain the complexities of the universe's gravitational interactions. One of the most significant examples of gravitational anomalies lies in the observation of galaxies. The rotation curves of spiral galaxies reveal a curious discrepancy. Stars far from the galactic center appear to move much faster than expected, based solely on the visible matter within the galaxy. This observation suggests that there is far more mass present than we can directly observe, leading to the hypothesis of dark matter, an invisible substance that exerts gravitational influence but has yet to be directly detected. This phenomenon challenges our understanding of gravity and prompts a reevaluation of how matter and energy are distributed throughout the universe. Gravitational anomalies have also been observed in the motion of satellites and spacecraft. For example, the Pioneer anomaly, first noticed in the early 1970s with NASA's Pioneer spacecraft, showed an unexpected acceleration toward the Sun as the spacecraft traveled farther from Earth. This mystery has led to various theories, including the possibility of thermal effects from the spacecraft's power source, but some scientists continue to explore deeper gravitational explanations. The analysis of galaxy clusters has also provided evidence of gravitational anomalies, such as in the case of the Bullet cluster, where two galaxy clusters collided. Gravitational lensing revealed a mismatch between the visible mass and the gravitational mass, strengthening the case for dark matter. These gravitational anomalies not only push the boundaries of our knowledge, but also open the door to new realms of scientific inquiry. They challenge our foundational theories and invite us to consider the possibility that the laws of physics may need to be adjusted to account for the strange and mysterious behavior of the universe. Each anomaly provides a glimpse into the unknown, offering scientists opportunities to revisit old models or create entirely new frameworks that can better explain the complexity of gravitational forces. As we continue to uncover these cosmic puzzles, we draw closer to a more profound understanding of the universe and the forces that govern its existence. Every new discovery, every new anomaly, brings us one step closer to unraveling the deepest mysteries of the cosmos. And as we venture further into space, we may just begin to understand the true nature of the gravitational forces that shape the stars, planets, and galaxies around us. The cosmic microwave background radiation, often considered a faint remnant of the Big Bang, offers more than just a snapshot of the early universe. It introduces a fascinating complexity regarding the gravitational forces that govern the universe's infancy. The subtle fluctuations in this radiation reveal potential gravitational waves, remnants of an epoch when space-time itself underwent rapid transformations. These fluctuations suggest phenomena linked to the inflationary period, a brief but profound era that occurred immediately after the Big Bang, where the universe expanded exponentially in fractions of a second. These faint cosmic bowls, etched into the very fabric of the universe, offer crucial insights not only into the origins of the cosmos, but also into the nature of gravity at the most extreme scales. The further we delve into these anomalies, the more we realize that they challenge established notions of gravitational behavior, pushing the boundaries of our understanding about how the universe's forces interacted in its infancy. Research in this field is ongoing, steadily bridging the gaps in our knowledge, and continues to offer a glimpse into the unseen forces that shape the cosmos at both the largest and smallest scales. Among the most compelling celestial objects studied in this context are quasars and pulsars. These enigmatic entities serve as invaluable guides in our exploration of the universe, revealing hidden details about cosmic phenomena that would otherwise remain out of reach. Quasars, short for quasi-stellar objects, are some of the brightest and most energetic sources of radiation observed in the cosmos. Powered by supermassive black holes lurking at the centers of distant galaxies, quasars offer a stunning example of how gravitational forces can concentrate energy in extraordinary ways. As matter spirals toward these supermassive black holes, it becomes trapped in their gravitational clutches, forming a swirling accretion disk. The immense heat generated by the friction and gravitational forces within this disk causes the matter to shine with immense brilliance, radiating across the entire electromagnetic spectrum. This process can make quasars so luminous that they outshine entire galaxies, allowing us to observe these distant objects from billions of light years away. Their extraordinary brightness offers a direct link to the early universe, providing an invaluable glimpse into the formation of galaxies just a few billion years after the Big Bang. What makes quasars particularly intriguing is their variability. Their brightness can fluctuate dramatically over short periods, suggesting rapid changes in their accretion processes or instability in the surrounding matter. These fluctuations challenge our understanding of the complex dynamics at play around black holes and within the galaxies they inhabit. The study of quasars not only enriches our understanding of supermassive black holes, but also sheds light on the larger processes of galaxy formation and evolution in the vastness of space. Pulsars, on the other hand, offer an entirely different but equally fascinating perspective on the universe. These neutron stars, the remnants of massive stars that have exploded in supernova, are compact, ultra-dense objects with a mass greater than the sun but compressed into a volume no larger than a city. Despite their relatively small size, pulsars are known for their rapid rotation, often spinning at remarkable speeds. As they rotate, they emit beams of radiation that sweep across space, much like the beam of a lighthouse. When Earth happens to lie in the path of one of these beams, we detect a regular pulse of radiation, hence the name pulsar. What is truly remarkable about pulsars is their extraordinary precision. Their consistent rotation and the regularity of their radiation emissions make them some of the most accurate timekeepers in the universe. Some pulsars are so stable in their periodicity that they serve as cosmic clocks, enabling scientists to study the fundamental laws of physics in extreme environments. Pulsars have been used to measure the effects of gravitational waves, ripples in space-time caused by massive events, such as the merging of black holes. By monitoring the precise timing of pulsar signals, scientists can detect minute variations caused by the passage of gravitational waves, offering an unprecedented window into the structure of space-time itself. Yet, for all their precision, pulsars remain enigmatic. Some display unexpected timing irregularities, known as glitches, in which their rotation rate suddenly changes. These glitches, which occur without warning, suggest alterations in the internal structure of the neutron stars and reflect the complex and dynamic nature of these objects. While much has been learned about pulsars, the exact mechanisms behind these glitches remain one of the many mysteries that continue to perplex astronomers and astrophysicists. Interestingly, pulsars that exist in binary systems where two stars orbit each other, further deepen our understanding of neutron stars and their environments. The interactions within these systems, where pulsars are often affected by the gravitational pull of a companion star, provide valuable clues about the conditions under which these stars form and evolve. Quasars and pulsars, despite their differences, both reveal the hidden forces at play in the universe. Quasars offer a window into the violent and energetic processes around supermassive black holes and the formation of galaxies. Pulsars, with their clock-like precision, allow us to explore the nature of matter under extreme conditions, while also offering a tool to study the very fabric of space-time itself. Together, these celestial objects provide a profound look into the universe's most mysterious and energetic phenomena, and continue to challenge and expand our understanding of the cosmos. Each discovery, each observation, brings us one step closer to unraveling the mysteries of the universe, yet leaves us with even more questions to answer. Pulsars, those mesmerizing, highly magnetized, and rapidly rotating neutron stars, continue to present an array of cosmic mysteries that captivate scientists and astronomers alike. These celestial bodies emit periodic bursts of electromagnetic radiation, and while their rhythmic pulses are predictable in many cases, there are instances where their behavior defies expectations, stirring up curiosity and intrigue within the astrophysical community. One of the most fascinating aspects of pulsars lies in the discovery of giant pulses, bursts of radio waves that are thousands of times brighter than regular pulses. These sudden and intense outbursts of energy remain one of the universe's unsolved puzzles. Researchers continue to debate their origin, as the mechanisms behind these giant pulses are still not fully understood. Some theories suggest that these bursts might be the result of unpredictable events or interactions within the pulsar's magnetic field, while others postulate that they could be linked to previously unobserved physical processes. Meanwhile, another enigmatic discovery is the observation of millisecond pulsars, which spin at astonishingly high rates, sometimes completing hundreds of rotations per second. This rapid spinning behavior not only challenges our understanding of how these stars form and evolve, but also provides valuable insight into the extreme conditions that exist within some of the densest objects in the universe. These pulsars could hold the key to unlocking deeper knowledge about stellar evolution and the underlying physical forces governing the cosmos. As astronomers delve deeper into these perplexing phenomena, pulsars reveal more than just the mechanics of their rotations. They force scientists to reconsider what they know about fundamental physics. The detection of pulsars in unusual settings, such as those found in dense stellar clusters or orbiting black holes, suggests that the environments surrounding these pulsars play a significant role in shaping their behavior. For example, pulsars in such environments may exhibit erratic rotational periods or emissions that are modulated in ways that traditional models cannot explain. These findings are far from trivial. They offer a chance to test the limits of known physics, challenging existing theories and providing new ways of thinking about the universe. In particular, pulsars located in unusual environments may harbor phenomena that are not present in more typical systems. Gravitational wave emissions, magnetic field interactions, and other extreme conditions could provide valuable insights into the nature of dark matter, the mechanics of black holes, and the intricacies of gravitational forces in ways that were previously unimaginable. Investigating these strange pulsars enriches our understanding of the universe, challenging established assumptions and paving the way for new lines of inquiry. Each oddball pulsar formation reveals further layers of complexity, propelling astrophysics forward and expanding our knowledge of the cosmos. With each discovery, we are reminded that there is still so much to learn and explore in the great expanse of space. At the heart of these cosmic enigmas lies dark matter, an invisible and elusive substance that comprises approximately 27% of the universe's total mass energy content. Despite its abundance, dark matter interacts minimally with electromagnetic forces, which means it neither emits, absorbs, nor reflects light. This lack of interaction makes it extraordinarily difficult to detect using traditional observational techniques. Consequently, scientists must infer its presence through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. One of the most significant pieces of evidence for dark matter comes from the study of galaxies. Observations show that galaxies spin at such incredible speeds that, without the gravitational pull of some unseen mass, they should fly apart. However, they remain intact due to the presence of dark matter. For example, when astronomers analyze the motion of stars and galaxies, they find that the amount of visible mass, such as stars and dust, is insufficient to explain the star's high velocities. This discrepancy strongly suggests that dark matter exists and surrounds galaxies, providing a type of cosmic glue that influences their formation and stability. Understanding dark matter is critical for several reasons. It plays a central role in the structure and evolution of the universe. Dark matter's gravitational influence during the early stages of galaxy formation helped shape the large-scale structure of the cosmos, affecting the formation of galaxies and clusters over billions of years. Moreover, dark matter impacts the cosmic microwave background radiation, the faint remnant glow from the Big Bang, which offers critical information about the early universe's expansion. The search for dark matter is not just a pursuit to solve one of the universe's greatest mysteries. It also opens doors to new realms of particle physics and cosmology. Although no definitive detection has yet been made, researchers have proposed several candidates for what dark matter might consist of. One of the leading contenders is weakly interacting massive particles, WIMPs, which are theorized to be particles that have mass and interact only weakly with ordinary matter. However, the elusive nature of WIMPs presents significant challenges in confirming their existence. Another intriguing possibility is the axion, a theoretical particle that arises from concepts in both particle physics and quantum mechanics. Axions are incredibly light and would also interact only minimally with regular matter, making them equally difficult to detect. Despite their elusive nature, the search for WIMPs and axions has prompted a surge of scientific research, including deep underground laboratories designed to detect rare interactions and advanced particle colliders that could potentially generate these particles. In the absence of direct detection, researchers have developed a range of innovative methods to infer the presence of dark matter. One of the most compelling techniques involves studying the rotation of galaxies. When scientists measure the speed at which stars orbit the centers of galaxies, they find that stars on the outer edges move much faster than expected based on the visible matter alone. This inconsistency suggests that some additional mass, presumed to be dark matter, is exerting a gravitational influence that holds these galaxies together. Gravitational lensing is another powerful tool in the search for dark matter. This phenomenon occurs when massive objects, such as galaxy clusters, bend the light from objects behind them. The distortion of light, a result of the curvature of spacetime predicted by Einstein's general theory of relativity, provides a way to map the distribution of dark matter. By analyzing the way light is bent and magnified, scientists can identify dark matter's presence even in the absence of direct visibility. Cosmic microwave background radiation also provides valuable insights into the presence of dark matter. The tiny fluctuations in temperature and density within this radiation contain vital information about the early universe. By studying these fluctuations, scientists can better understand the distribution of mass, including dark matter, in the early cosmos, contributing to a more comprehensive picture of the universe's overall structure. Together, these methods provide growing evidence for dark matter's role in the universe. While the substance itself remains invisible, scientists continue to piece together its presence through the gravitational influence it exerts on galaxies, the bending of light, and the clues hidden in the remnants of the Big Bang. As research progresses, our understanding of dark matter is poised to expand, ultimately offering new insights into the evolution of the universe itself. The nature of dark matter remains one of the most tantalizing puzzles in modern physics. What is this mysterious substance that accounts for a large portion of the universe's mass? As the search continues, astronomers and physicists remain focused on answering this question, knowing that each new discovery brings them closer to unraveling one of the greatest mysteries of our time. Scientists continue to explore groundbreaking ideas that challenge the very foundations of our understanding of the cosmos. And one such area of intrigue is the nature of gravity. While the traditional view of gravity, as outlined by Newton and Einstein, has served us well for centuries, a growing number of researchers are turning their attention to theories that question the very principles upon which this force is built. Among these, one of the more provocative alternatives is modified Newtonian dynamics, MMOND, which proposes that the gravitational behavior of objects at large cosmic scales might not adhere to the rules we've always relied on. Rather than attributing certain mysterious cosmic phenomena to the elusive substance known as dark matter, MMOND suggests that adjusting our comprehension of gravity could explain these occurrences. This theory challenges the conventional explanation of dark matter, which is believed to exist because of its unseen gravitational effects on galaxies and clusters. Yet, MMOND's proposition is far from mainstream, as it lacks sufficient observational backing to gain widespread acceptance in the scientific community. Nevertheless, it serves as an important piece of the puzzle that encourages further investigation into the mysteries of our universe. As researchers continue to analyze data from various cosmic phenomena, including the cosmic microwave background radiation and the distribution of galaxies, these findings will inevitably continue to shape and refine our theories on the makeup of dark matter. In the broader context, each theory, whether it leans toward dark matter or gravity modifications, adds layers to the ever-expanding tapestry of scientific hypotheses. These ideas collectively push the boundaries of physics, offering new directions for understanding the unseen forces that shape the universe. What remains certain, however, is the undeniable role of dark matter in the cosmos. Although its true nature remains elusive, dark matter is integral to the formation of galaxies, exerting influence over the way structures in space are arranged and how they evolve over time. The expansion of the universe itself provides further evidence of this unseen force at work. However, this expansion is not a steady, gradual process, but one that is rapidly accelerating, pushing galaxies apart at increasing rates. This cosmic acceleration is not driven by any known matter, but by a mysterious entity, dark energy. Dark energy, which is thought to constitute approximately 70% of the total energy density of the universe, has a repulsive force that acts in opposition to gravity. While gravity pulls matter together, dark energy pushes the fabric of space itself apart, accelerating the separation of galaxies. This accelerating expansion suggests that, while matter and gravity play vital roles in the formation of the universe, dark energy is the dominant force behind its ongoing expansion. It is as though dark energy is an invisible hand that continually stretches the vastness of space, overcoming the attractive pull of gravity. As time progresses, the effect of dark energy becomes increasingly dominant, with its influence growing stronger as the density of matter in the universe decreases. In essence, the more the universe expands, the more dark energy dictates the rate of that expansion, making it a force that is both pervasive and essential for understanding the future evolution of the cosmos. Dark energy's role in shaping the universe raises critical questions about the ultimate fate of our cosmos. What will happen to the universe as its expansion continues? Will it eventually slow down, reach a steady state, or accelerate indefinitely? Some theories propose that the universe's expansion could continue at an ever-increasing pace, leading to a scenario known as the Big Rip. In this eventuality, the expansion could become so extreme that galaxies, stars, and even atoms would be torn apart by the relentless pull of dark energy, resulting in the dissolution of all matter as we know it. While these questions remain unresolved, the study of dark energy is one of the most exciting and important areas of modern cosmology. Scientists are utilizing cutting-edge telescopes and space missions to observe distant galaxies and phenomena, all in an effort to better understand the behavior of dark energy and its impact on the universe. Through these observations, they hope to refine existing theories and gain a clearer picture of the cosmic forces that govern the universe. As our understanding of dark energy deepens, it is poised to answer some of the most profound questions in science. What is the true nature of dark energy? How does it shape the cosmic environment? And perhaps most importantly, what does its influence mean for the future of the universe? Currently, many competing theories about dark energy remain under active investigation. One possibility is that dark energy is a constant, an inherent energy density that fills space uniformly. This idea, known as the cosmological constant, was first introduced by Albert Einstein more than a century ago. Alternatively, some scientists speculate that dark energy could vary across time and space, leading to different effects on the expansion of the universe over time. These possibilities, whether dark energy is constant or variable, remain open questions in the field of cosmology. But what is clear is that dark energy will continue to play a crucial role in our understanding of the universe's ultimate destiny. As scientists continue to unravel its mysteries, they move closer to answering some of the most fundamental questions about the very nature of existence, the forces that govern it, and the future of everything we know. Scientists have long been captivated by the relationship between dark energy and the fundamental forces that shape our universe. Dark energy, a force that remains an enigma, seems to be intricately tied to gravity, the force that governs how matter behaves. But what if there's a deeper connection between them? Could dark energy and gravity share hidden properties that could revolutionize our understanding of the cosmos? Exploring this link between dark energy and gravity could provide groundbreaking insights into the large-scale structure of the universe. It may help clarify one of the universe's most puzzling phenomena, the accelerated expansion of galaxies. Instead of galaxies slowing down due to the force of gravity, as we might expect, they're flying apart faster and faster. What's driving this phenomenon and why? The implications of dark energy are profound. As it propels the acceleration of the universe's expansion, it raises questions about the ultimate fate of the cosmos. Will the universe continue to stretch out into an infinite void where galaxies drift further apart, isolated from one another? This idea, known as the Big Freeze, has intrigued cosmologists. On the other hand, could dark energy eventually lose its influence, allowing the universe to contract in a dramatic reversal, a scenario referred to as the Big Crunch? These concepts aren't just abstract, they are active areas of research. Scientists around the world are working tirelessly to understand how dark energy will shape the future of everything we know. The exploration of dark energy has become much more than a pursuit of knowledge. It's a challenge to our very understanding of reality itself. Every new discovery brings us closer to unraveling these profound mysteries, and every question answered seems to give rise to a new set of even deeper inquiries. At the same time, scientists distinguish dark energy from its elusive counterpart, dark matter. Though both are invisible and mysterious, they serve entirely different roles within the universe. Dark matter, despite being invisible to the naked eye, can be detected through its gravitational effects on visible matter. It behaves like a cosmic glue, holding galaxies and galaxy clusters together. Researchers can observe how galaxies move and how they are distributed across the universe, inferring the presence of dark matter, based on how galaxies spin or cluster in unexpected patterns. If a galaxy spins faster than expected based on visible matter alone, dark matter is likely at play, influencing its dynamics. In contrast, dark energy seems to have the opposite effect. While dark matter draws things together, dark energy is pushing galaxies apart, accelerating the expansion of the universe. Scientists are working to understand dark energy's influence through observations of the cosmic microwave background radiation, the faint glow left over from the Big Bang, and the distribution of supernovae across the cosmos. These observations indicate that the expansion rate of the universe is not slowing down, as one might expect due to gravity, but speeding up instead. This accelerated expansion is one of the key characteristics of dark energy. To simplify the distinction, dark matter is inferred through gravitational effects, whereas dark energy is studied by observing the universe's expanding nature. While these phenomena are fundamentally different, they both offer critical insights into the underlying workings of the cosmos, and scientists are developing novel methods to study them. This ongoing research not only enhances our understanding of these two mysterious entities, but also sheds light on the broader nature of the universe itself. Each discovery acts like a new brushstroke in the cosmic painting, bringing us closer to understanding how dark matter and dark energy shape the structure of everything that exists. As scientists continue their work, they uncover the subtle complexities that drive cosmic interactions, challenging our previous models and guiding the way for future explorations of the universe's most hidden realms. Across the globe, researchers are employing a variety of innovative methods to probe these elusive phenomena. Some of the most advanced experiments rely on ground-based and space-based observatories, which capture faint signals from the farthest reaches of space. These observatories aim to detect the subtle influences of dark matter and dark energy on visible matter, providing a more detailed understanding of the universe's invisible components. One of the key tools in this pursuit is the Large Hadron Collider, LHC, in Geneva, Switzerland. This cutting-edge particle accelerator propels particles to near light speeds, colliding them to explore a range of fundamental questions, including the existence of dark matter. Researchers are particularly focused on identifying weakly interacting massive particles, WIMPs, which are considered strong candidates for dark matter. By analyzing the results of these high-energy collisions, scientists hope to uncover new particles that could offer insight into the dark sector of the universe. In parallel, astrophysical surveys are playing an essential role in this research. Observatories such as the Sloan Digital Sky Survey, SDSS, and the European Space Agency's Euclid mission are mapping the distribution of galaxies and galaxy clusters across vast stretches of the universe. By studying the gravitational effects of dark matter on visible matter, these surveys are helping to reveal patterns that point toward the presence and properties of dark matter throughout the cosmos. Meanwhile, the study of dark energy continues to gain momentum. One of the most significant sources of information is the cosmic microwave background radiation, which provides crucial data about the history of the universe's expansion. Gravitational wave observatories, such as the Laser Interferometer Gravitational Wave Observatory, LIGO, also contribute valuable insights. Though designed primarily to detect ripples in spacetime caused by collisions between black holes or neutron stars, these observatories also offer an enhanced understanding of cosmic events influenced by dark matter and dark energy. Each of these efforts, whether focused on particle physics or astrophysical observation, contributes a crucial piece to the intricate puzzle of dark matter and dark energy. With each new breakthrough, we edge closer to unlocking the mysteries surrounding these phenomena. As our knowledge grows, so too does our understanding of the cosmos, one step at a time. The discovery of dark matter and dark energy has undoubtedly transformed our view of the universe. These two components, while invisible, play a pivotal role in shaping the cosmos. Dark matter, which does not emit light or energy, accounts for roughly 27% of the universe's total mass energy content. In contrast, dark energy, the force driving the accelerated expansion of the universe, makes up about 73%. Together, they challenge traditional concepts of gravity and the structure of the universe, reshaping our understanding of fundamental forces. One of the most profound implications of these discoveries lies in how they challenge our understanding of gravity itself. According to Newtonian physics and Einstein's theory of general relativity, gravity is a force that is directly proportional to mass. The more mass, the stronger the gravitational pull. However, the presence of dark matter and dark energy forces us to rethink these fundamental principles. As we continue to investigate these invisible forces, our comprehension of gravity and the structure of the universe is being redefined, laying the groundwork for a new era of cosmological exploration. However, dark matter introduces a profound complexity into the picture. Though we cannot directly observe it, its presence is unmistakably felt through its gravitational effects on galaxies. For instance, the way galaxies rotate and cluster together provides compelling evidence that something unseen is influencing their motion. The inclusion of dark matter in our cosmic models forces scientists to reassess some of the most fundamental laws of physics. It opens the door to new theories that could explain how dark matter interacts with the matter and energy we encounter in our everyday lives. Alongside this mystery lies dark energy, an equally perplexing force that raises even more profound questions. If the universe is expanding at an ever-accelerating rate, what is the underlying cause of this cosmic acceleration? Current models of cosmology must account for this unexplained expansion, compelling astronomers to investigate the nature of dark energy and its role in the universe's future. Will this relentless expansion continue indefinitely, stretching the fabric of space-time to a point where the universe becomes a cold, dark void? Or might it lead to more dramatic scenarios, such as a big rip, where the very structure of the universe is torn apart at its seams? Each of these possibilities forces a reevaluation of space-time itself and raises unsettling questions about the ultimate fate of everything in existence. As researchers continue to investigate the enigma of dark matter and dark energy, our models of the universe are rapidly evolving. Every new discovery not only deepens our understanding of the cosmos, but also sparks fresh debates about alternative theories like modified gravity or string theory. Each breakthrough carries the potential to unravel more mysteries, unveiling fundamental truths about how the universe operates. The more we discover, the more we realize that our story of cosmology is far from complete. In fact, every discovery reminds us of the vast, unexplored unknowns that lie ahead, urging scientists and enthusiasts alike to remain open-minded about the cosmic mysteries yet to be uncovered. The journey to understanding dark matter and dark energy is still in its infancy, and the road ahead promises even greater revelations. This quest for knowledge began with a series of groundbreaking astronomical and physical discoveries. One pivotal moment in the early 20th century changed the course of cosmology forever. Astronomer Edwin Hubble made the astonishing discovery that galaxies were not merely drifting through space, but were actually moving away from us. This was confirmed through the observation of a red shift in the light from distant galaxies, which signaled that they were receding from our own. Hubble's groundbreaking work led to the formulation of Hubble's law, which definitively suggested that the universe is expanding. As astronomers delved deeper into the mysteries of cosmic phenomena, they began to notice peculiar behaviors in galaxy clusters. In the 1930s, Swiss astronomer Fritz Zwicky, investigating the Coma cluster, noted something strange. The visible mass of the cluster was insufficient to explain its gravitational pull. To account for this discrepancy, he proposed the existence of an unseen form of matter, which he called Dunkel Matter, dark matter. Zwicky's hypothesis laid the groundwork for what would become one of the most significant areas of modern astrophysical research. By the late 20th century, technological advancements such as improved telescopes allowed scientists to probe the universe with greater precision. One such discovery was the phenomenon of gravitational lensing. This occurs when light from distant galaxies bends around massive objects, creating a visual effect similar to a lens. The amount of mass needed to produce this bending was far greater than the visible mass in these regions, providing additional indirect evidence for the existence of dark matter. Despite advancements in technology and our ability to observe the cosmos more clearly, dark matter remains elusive and undetectable by conventional means. Nevertheless, it is estimated to make up about 27% of the universe's total mass energy content, far outweighing the visible matter we can see. At the same time, another great cosmic mystery began to unfold. In the late 1990s, two independent research teams made a stunning discovery. The expansion of the universe was not slowing down, as had long been believed, but was accelerating. This shocking revelation led to the introduction of dark energy, a mysterious force that is believed to account for roughly 73% of the universe's energy content. Both dark matter and dark energy present some of the greatest challenges to modern cosmology, inspiring intense research and speculation as scientists strive to unlock their secrets. The potential discovery of entirely new forms of matter or energy would revolutionize our understanding of the universe. Today, scientists classify the matter we can see, stars, planets, and galaxies, as baryonic matter, which accounts for a mere fraction of the universe's composition. The vast majority of the universe is thought to be made up of dark matter, a substance that interacts with ordinary matter through gravity but does not emit, absorb, or reflect light, making it invisible to our detection methods. We can only infer its existence through its gravitational effects on the visible universe. If new forms of matter or energy were discovered, it could indicate that our current understanding of physics is incomplete. Such a revelation would force a profound re-examination of fundamental theories. The implications of this could extend far beyond the realm of theoretical physics. For instance, discovering a new type of particle that could store energy more efficiently could lead to revolutionary advances in energy production. Similarly, uncovering a new medium for transmitting information could transform communications technology, leading to faster and more secure data transfer methods. The impact of such discoveries could even extend to space exploration. Advances in propulsion technology driven by a better understanding of exotic forms of matter might allow us to reach distant worlds that are currently beyond our grasp due to energy limitations. On a grander scale, the discovery of these new entities could provide crucial insights into the nature of the universe's expansion. Understanding the forces that drive the acceleration of this expansion is essential to unlocking the mysteries of dark energy. It could even give us a clearer picture of the universe's ultimate fate. Will this expansion continue indefinitely, forever stretching the fabric of space-time? Or will other, more exotic forces come into play, shaping the destiny of everything we observe? In any case, the exploration of dark matter and dark energy promises to be a key chapter in the ongoing saga of our cosmic understanding. Superclusters, the colossal formations that stretch across vast expanses of space, hold a key position in the universe's cosmic architecture. These immense structures, consisting of groups or clusters of galaxies, are bound together by the invisible but powerful force of gravity. A single supercluster can span millions of light years, containing hundreds or even thousands of galaxies, each with its own set of stars, gas, and dark matter. Together, they form a vast, interconnected network that helps define the large-scale structure of the universe. Understanding superclusters is not just a matter of uncovering the raw scale of the cosmos, but it also holds the potential to unlock deeper knowledge about the forces that govern the universe and our place within it. Such discoveries could revolutionize how we think about the universe itself. They have the power to connect the seemingly disparate dots between the large-scale structure of the cosmos and the fundamental forces that shape it. By studying these extraordinary structures, scientists might discover unified theories that reconcile gravity with the forces of quantum mechanics, leading to a more complete understanding of how the universe works at both its largest and smallest scales. These groundbreaking revelations could also capture the imagination of the public, sparking interest in scientific exploration on an unprecedented scale. They could inspire a new generation of scientists, thinkers, and dreamers to dive deeper into the mysteries that lie beyond our everyday experiences. As we rethink our place in the vast expanse of space, these findings could instill a profound sense of wonder and curiosity, motivating individuals to explore not just the universe itself, but also our own nature and existence within it. The search for new forms of matter and energy, unknown yet critical to our understanding of reality, could shape the future trajectory of science and human progress. These discoveries offer more than just knowledge. They offer a sense of connection to the cosmos, a sense of awe that transcends disciplines and invites a shared quest for knowledge and discovery. A supercluster, one of the largest structures we know in the universe, is a vast collection of galaxies, tightly bound together by the force of gravity. These superclusters can stretch across millions of light years, revealing the immense scale of the cosmos. A prime example is the Laniakea supercluster, the cosmic structure that contains our own Milky Way galaxy. Spanning over 100 million light years and containing approximately 100,000 galaxies, Laniakea serves as a pivotal piece in the larger cosmic puzzle. It is not just a cluster of galaxies, but a dynamic system, interconnected with others through invisible threads of dark matter and gas, forming a cosmic web that stretches throughout the universe. Superclusters, like the Laniakea, offer more than just a spectacular visual of the cosmos. They allow us to classify the universe's grand structures based on their size, number of galaxies, and the density of the clusters within them. Some superclusters are rich, containing a high density of galaxies and galaxy clusters, while others are poor, with more sparse galaxy populations. The Virgo supercluster, home to the famous Virgo cluster, is another example of a key supercluster in our local universe. With around 2,000 galaxies contained within a region of about 15 million light years, Virgo has a significant role in our local cosmic neighborhood. Its mass influences the motion of nearby galaxies, shaping their movements through the gravitational pull it exerts. Then there is the Perseus-Pisces supercluster, an extraordinary formation stretching over 150 million light years and housing numerous galaxy clusters. Among them is the Perseus cluster, one of the most massive galaxy clusters known to science. The sheer scale and energy of this supercluster are remarkable, as it hosts active galactic nuclei and some of the brightest galaxies observable from Earth. Moving further into the depths of the southern sky, we encounter the Shapley supercluster. Situated about 600 million light years away, it is one of the most densely populated regions in the universe, housing over 1,000 clusters of galaxies. These superclusters are not mere collections of galaxies. They represent a deeper, interconnected structure, a reflection of the underlying forces at play in the universe. The study of these vast entities not only sheds light on the gravitational forces that shape the cosmos, but also offers a window into the mysterious world of dark matter and dark energy. These two elusive components, making up the majority of the universe's mass and energy, remain largely hidden from view, but superclusters act as essential laboratories for scientists studying them. As scientists continue to explore these immense structures, they are uncovering new insights into the universe's evolution. Superclusters are not just monumental in size, they also reveal the intricate, almost web-like structure that defines the cosmic landscape. The universe as we observe it is far from a uniform, smooth expanse. Instead, it is a complex network where matter is unevenly distributed, with superclusters acting as the nodes in this vast cosmic web. These superclusters are interconnected by long filaments of dark matter and gas, creating a structure that resembles a giant cosmic spider's web. This arrangement plays a critical role in shaping the dynamics of the universe. Superclusters influence the motion and evolution of galaxies, triggering the formation of new stars or causing galaxies to merge and change shape. Through these processes, superclusters offer a glimpse into how the universe has evolved over billions of years and may continue to evolve in the future. By studying them, scientists gain valuable insights into the origins of galaxies, the growth of cosmic structures, and the effects of dark energy on the expanding universe. The scale of superclusters underscores not only the depth of the universe, but also the complexity of the forces at play. They represent some of the largest known structures, yet they are just one part of a grand continuum that stretches from smaller galaxy clusters to enormous cosmic voids. These formations play a critical role in the overarching structure of the universe, acting as pillars that support the universe's expansive framework. Researchers study superclusters to understand how galaxies cluster together and how gravitational forces shape their movement through space. These cosmic structures also offer a key to understanding the evolution of the universe and its future trajectory. Superclusters are not just about size, they are also about the relationships between galaxies and how they interact across vast distances. These interactions affect how galaxies form, evolve, and ultimately shape the structure of the universe. By studying superclusters, scientists continue to piece together the puzzle of our universe's past and future. Understanding how these giant structures fit into the larger framework of the cosmos helps us appreciate the complexity of the universe itself and our role within it. In the grand scheme of the universe, superclusters are monumental markers, guiding our exploration of the cosmos and helping us unravel the forces that define its very fabric. Each discovery, each new piece of the puzzle, offers a deeper understanding of the universe's creation, its ongoing evolution, and its ultimate fate. As we continue to investigate these cosmic structures, we uncover not only the mysteries of the universe, but also the possibility of a future where our understanding of reality is shaped by the forces that govern it. The proximity of galaxies within superclusters creates an environment where the exchange of material is common, leading to a dynamic and complex system that significantly contributes to the variety of galaxy types we observe today. Superclusters, massive groupings of galaxies bound by the invisible force of gravity, continue to surprise scientists as they delve deeper into the universe's formation and large-scale structure. Through these investigations, researchers are constantly uncovering new layers of understanding, challenging previously held beliefs about cosmic evolution and the distribution of matter throughout the universe. One such revelation came with the discovery of the Hercules Corona Borealis Great Wall, a colossal supercluster that has now been recognized as the largest known structure in the universe. This discovery reshapes our understanding of how matter is distributed across vast distances and provides new insights into the forces at play in the formation of large-scale structures. By examining the distribution of galaxies across superclusters, scientists can gain a clearer understanding of the universe's early stages, its expansive nature, and the intricate interplay between galaxies over cosmic time. Each new discovery adds a vital piece to the cosmic puzzle, shedding light on the hidden forces that shape the universe. At the core of this study is the concept of gravity, the invisible thread that governs the motion and interaction of galaxies. Through the study of the cosmic microwave background, CMB, radiation, scientists have been able to peer back in time, gathering crucial information about the universe's formation. The CMB, a faint glow of radiation that permeates the cosmos, is a remnant of the Big Bang, offering a snapshot of the universe roughly 380,000 years after its inception. At this early stage, the universe had cooled enough for hydrogen and helium atoms to form, allowing light to travel freely for the first time. The CMB reveals a universe that was nearly uniform, with slight fluctuations in temperature and density. These variations, though subtle, offer key insights into the distribution of matter in the early universe, serving as a map that traces the evolution of structures like superclusters over billions of years. These fluctuations reflect the gravitational forces that shape the universe, with denser regions attracting more matter over time, leading to the formation of galaxies and their clusters. By studying the CMB, scientists can trace how matter has coalesced to form the large-scale structure of the universe, including the locations of superclusters. As technology advances, astronomers are able to gather increasingly detailed information from the CMB, providing new insights into the universe's expansion and the role of dark energy in shaping cosmic structures. These findings not only help to map the formation of superclusters, but also reveal how they continue to evolve as the universe expands. The boundaries of superclusters, where regions of intense galactic activity meet vast cosmic voids, offer an exciting frontier for scientific exploration. Superclusters themselves are massive conglomerates of galaxies, often containing hundreds or even thousands of individual galaxies, bound together by gravity. These immense structures create a gravitational pull that shapes their surroundings, but at their edges, one can find intriguing phenomena that offer a deeper understanding of the universe's evolution. One of the most fascinating features of supercluster boundaries is the presence of cosmic voids. vast expanses of space that contain few, if any, galaxies. These voids are stark contrasts to the dense galaxy clusters that dominate the interiors of superclusters. The existence of such voids provides critical clues about the structure of the universe, revealing the web-like architecture formed by dark matter and dark energy, which influences the distribution of galaxies and superclusters. Additionally, these boundaries serve as regions of intense dynamic activity. Galaxies located near the edges of superclusters are subject to significant gravitational interactions, which can result in galaxy collisions and mergers. These cosmic events often lead to the creation of new structures, such as starburst galaxies, regions where intense star formation occurs as gas and dust are compressed by gravitational forces. These high-energy interactions also produce X-rays and other forms of radiation, which can be studied using advanced space telescopes to further understand the energetic nature of these phenomena. Moreover, supercluster boundaries also provide an ideal environment for studying primordial acoustic oscillations, fluctuations in the density of the early universe. These oscillations left an imprint on the distribution of galaxies, and studying their manifestation at the edges of superclusters offers invaluable information about the age of the universe, its expansion, and the role of dark matter in cosmic evolution. These cosmic echoes reveal much about the universe's infancy, helping scientists piece together its complex history. The study of superclusters continues to evolve, with scientists employing of observational and theoretical methods to understand their formation and ongoing development. One of the key tools in this research is the use of advanced telescopes, which allow astronomers to observe vast portions of the sky and collect data on galaxy distributions, their redshifts, and the velocities at which they are moving away from us. This data helps to map the vast cosmic structures and understand how superclusters evolve over time. Computer simulations also play a crucial role in this research. By creating detailed models of the universe based on the laws of physics, scientists can simulate the processes that lead to the formation of superclusters. These models take into account gravitational forces, dark matter, and other cosmic factors, providing a virtual environment to test various theories and scenarios. When these simulated outcomes are compared with actual observations, they offer new insights into the processes that govern the formation and growth of superclusters. Another vital aspect of supercluster research involves the study of the cosmic microwave background, CMB, radiation, a remnant of the early universe. By examining tiny fluctuations in the CMB, scientists can infer the conditions of the universe shortly after the Big Bang. These fluctuations have a lasting impact on the distribution of galaxies and superclusters, shaping their formation over billions of years. Understanding the CMB in this context helps to contextualize superclusters within the broader narrative of cosmic evolution, providing a clearer picture of how these immense structures developed. Large-scale astronomical surveys have also proven invaluable in the study of superclusters. By mapping billions of galaxies, these surveys generate vast amounts of data, which help scientists identify patterns in galaxy distributions and uncover relationships between galaxies within superclusters. This information is continuously expanding our understanding of how these colossal structures came to be, offering a more comprehensive view of the universe's ongoing expansion. At the heart of supercluster dynamics lies the mysterious force known as dark energy, which makes up roughly 70% of the universe's total energy density. Though its exact nature remains elusive, dark energy's effects are observable, particularly in the context of the accelerated expansion of the universe. As some of the largest structures in the cosmos, superclusters provide valuable evidence of dark energy's influence. Their movement and the way they interact with other cosmic structures offer essential clues about how dark energy is shaping the universe's future. In conclusion, the study of superclusters and the forces that shape them, especially gravity, dark matter, and dark energy, continues to reveal fascinating insights into the nature of our universe. Through a combination of observational techniques, computer simulations, and the study of ancient cosmic radiation, scientists are piecing together the complex history of these massive structures, offering a deeper understanding of how the cosmos has evolved and will continue to do so in the future. As our technology and understanding advance, we are poised to uncover even more about the hidden forces that govern the universe's growth and evolution. The cosmic microwave background radiation, CMB, represents a crucial piece of the puzzle in understanding the vast and intricate history of the universe. Often referred to as the afterglow of the Big Bang, the CMB provides a snapshot of the universe in its infancy, offering insights into the forces that have shaped the cosmos as we know it. This faint, pervasive radiation is not just a lingering echo of the early universe, but a window through which astronomers and cosmologists are able to peer back in time, exploring how dark energy and other cosmic forces have influenced the evolution of galaxies, superclusters, and the entire structure of the universe. The CMB itself is a remnant of the moment when the universe began to cool after the Big Bang, some 13.8 billion years ago. At that time, the universe was a hot, dense soup of particles, with light unable to travel freely due to the scattering of photons by electrons and protons. As the universe expanded and cooled, it eventually reached a temperature where atoms could form, allowing photons to travel without interference. This marked the moment when the universe became transparent, and the light from that time, the CMB, continues to permeate the universe today, detectable in every direction we look. With a temperature of about 2.7 degrees Kelvin, just above absolute zero, the CMB serves as a relic of the early universe, providing valuable clues about its birth and subsequent expansion. What makes the CMB particularly fascinating are the slight temperature fluctuations found within it. These fluctuations, although minuscule, are of immense importance. They reveal the density variations in the early universe, tiny ripples in the fabric of space-time, that eventually led to the formation of galaxies, clusters, and the vast cosmic filaments we observe today. These primordial fluctuations are the seeds of structure in the universe, offering a glimpse into the processes that governed its formation. As the universe continued to evolve, these initial differences in density grew into the large-scale cosmic structures we see, influenced by complex forces such as dark energy, dark matter, and gravity. Researchers have harnessed the CMB to answer some of the most fundamental questions about the universe. By studying its properties, scientists can determine key details about the universe's age, its overall composition, and its geometry. More importantly, the CMB provides vital evidence supporting the Big Bang theory, the prevailing explanation for the origin of the universe. Missions such as the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have provided astronomers with an unprecedented level of precision in measuring the CMB's temperature fluctuations, helping to refine our understanding of cosmic inflation, the rapid expansion of the universe that occurred in the moments following the Big Bang. But the CMB is just one aspect of the story. The universe itself is a dynamic and ever-evolving entity, and recent advancements in technology are allowing scientists to explore its complexities in unprecedented ways. The study of large cosmic structures, such as superclusters, provides further insight into how the universe has evolved over cosmic time. Superclusters are vast groupings of galaxies that span millions of light years, and understanding their formation and behavior helps astronomers piece together the grand cosmic tapestry. The dynamics of these structures are heavily influenced by dark energy, the mysterious force believed to be driving the accelerated expansion of the universe. Voids, vast expanses of space with very few galaxies, are another key feature in this cosmic landscape. These voids can span hundreds of millions of light years and are often bordered by clusters and superclusters of galaxies. While their emptiness might suggest they are insignificant, voids play a crucial role in our understanding of the universe's structure and evolution. They serve as a kind of cosmic blueprint, revealing how matter is distributed on large scales. According to current cosmological models, the universe has a sponge-like structure, with vast filaments of galaxies interwoven with empty spaces. By studying voids, scientists gain valuable insights into the gravitational forces that shape these cosmic structures and influence their formation. Interestingly, voids are also linked to the phenomenon of dark energy. These regions of lower density appear to be affected differently by the energy driving the universe's expansion compared to denser areas. As a result, voids provide a natural laboratory for studying how dark energy influences the universe's expansion and how galaxies behave within and around these voids. The study of voids also holds implications for understanding the formation of elements and the processes that preceded the large-scale structure of the universe. In the early stages of cosmic evolution, primordial fluctuations in density led to the clustering of matter, and voids mark the regions where matter was more deficient, offering clues about the paths of cosmic evolution. With advancements in technology, our ability to study these cosmic structures is rapidly improving. Powerful telescopes equipped with advanced sensors, along with innovative techniques like adaptive optics and radio interferometry, are enabling astronomers to collect more detailed and precise data than ever before. These technologies allow scientists to correct for the blurring effects of Earth's atmosphere and combine signals from multiple telescopes to create clearer images of distant cosmic phenomena. Additionally, the rise of data processing capabilities, including machine learning algorithms, is playing a crucial role in analyzing the vast amounts of data collected from space-based observatories like the Hubble Space Telescope and the upcoming James Webb Space Telescope. These advancements in data processing are allowing researchers to map the distribution of galaxies within superclusters and better understand their formation and evolution over cosmic time. Computational simulations have also made it possible to model the complex dynamics of superclusters, helping scientists predict how these massive structures will evolve under the influence of dark matter and dark energy. By simulating the gravitational interactions between these structures, researchers can gain new insights into the large-scale behavior of the universe. Furthermore, the integration of multi-wavelength observations across radio, optical, infrared, and X-ray wavelengths has transformed our understanding of cosmic structures. Each wavelength reveals different aspects of these structures, from the hot gas surrounding galaxies to the faint light emitted by distant stars. By combining observations from multiple wavelengths, scientists now have a more comprehensive view of superclusters, providing a deeper understanding of their composition and evolution. In summary, the study of the cosmic microwave background radiation, voids, and superclusters is revolutionizing our understanding of the universe. These cosmic structures, along with the technologies and techniques used to explore them, are helping us answer some of the most profound questions about the nature of the cosmos. As we continue to advance our tools and methods, we are drawing ever closer to unraveling the mysteries of cosmic evolution and uncovering the fundamental laws that govern the universe. The more we learn, the more we realize how much there is still to discover. Cold spots in the universe are a captivating mystery for astronomers and cosmologists alike. These regions, where temperatures are notably lower than the surrounding space, present a unique opportunity to probe the hidden structures and dynamics of the cosmos. One of the most fascinating aspects of cold spots is their potential connection to the grand architecture of the universe. Some theories suggest that these colder patches could be remnants of the early formation of cosmic structures, offering clues about how galaxies came into existence and how they are distributed across the universe. These anomalies may not only reveal variations in temperature, but they could also provide critical insights into the more elusive phenomena like dark energy, the force believed to be responsible for the universe's accelerated expansion. Among the most prominent cold spots is the so-called cold spot in the cosmic microwave background, CMB, located in the southern hemisphere of the sky. This particular cold spot has intrigued scientists because of its unusual characteristics, raising profound questions about the early universe's behavior. Several hypotheses have emerged to explain this anomaly. One widely discussed theory suggests that the cold spot may be the result of a supervoid, a massive and almost empty region of space devoid of galaxies. The presence of such a supervoid could distort the cosmic radiation we observe, causing the temperature in that area to drop. Alternatively, some researchers speculate that this cold spot could be a remnant of the inflationary period, the era shortly after the Big Bang, when the universe expanded at an extraordinary rate. Others suggest that the cold spot might offer evidence of the existence of parallel universes as part of the multiverse theory, raising mind-bending questions about the nature of reality itself. By studying these cold spots, scientists aim to unravel the deeper mysteries of the universe, exploring not just the remnants of the Big Bang, but also the fundamental forces that shape our existence. These cold regions may be the key to understanding how cosmic structures evolve and perhaps even unlocking entirely new phenomena that could transform our understanding of space and time. The cold spots in the CMB are a reminder that even the smallest fluctuations in temperature can carry the weight of the universe's most profound secrets. The cosmic microwave background radiation, or CMB, serves as a kind of cosmic fossil, providing a snapshot of the universe from a time when it was only 380,000 years old, just moments after the Big Bang. At this point in the universe's history, it transitioned from being a dense, hot fog of particles to a transparent expanse, allowing light to travel freely through space. This faint glow of microwave radiation fills all of space, acting as a record of the conditions and characteristics of the early universe. It is this radiation that scientists use to uncover the timeline of cosmic evolution, giving us a glimpse into the birth of the stars, galaxies, and everything in between. By carefully analyzing the minute fluctuations in temperature found in the CMB, scientists can determine the density variations of matter and energy from the early universe. These variations are the seeds from which galaxies grew, influenced by the gravitational forces that acted on the early matter. The study of these fluctuations also provides valuable insights into the composition of the universe. For example, researchers can calculate the distribution of normal matter, and dark energy, three critical components that govern the universe's behavior. The CMB also provides scientists with key data to refine our understanding of cosmological parameters like the age of the universe and its geometry. Current CMB observations suggest that the universe is expanding and that it has a flat geometry on large scales. This expansion has been ongoing for approximately 13.8 billion years, a timeline that frames the history of cosmic evolution, including the birth and development of galaxies, stars, and planetary systems. In addition to its cosmological implications, the CMB plays a crucial role in testing theories related to inflation, a period of rapid expansion just after the Big Bang that could hold the key to understanding the physics governing the universe's earliest moments. Fluctuations in the CMB are particularly important when it comes to understanding galaxy formation. These tiny variations in temperature across the CMB map represent differences in density across the early universe. In regions where the density of matter was slightly higher, gravity began to pull matter together, eventually leading to the formation of stars and galaxies. These fluctuations are the remnants of sound waves that traveled through the primordial plasma in the universe's early days. As these sound waves created areas of compression and rarefaction, regions with higher density later evolved into gravitational wells that attracted gas and dark matter. This process eventually led to the formation of galaxies, which continue to evolve and shape the universe we observe today. In essence, cold spots in the CMB are not just random anomalies, but significant markers in the larger story of the universe's creation and evolution. Each of these cold regions holds a potential key to understanding the forces and structures that have shaped the cosmos since the earliest moments after the Big Bang. By studying them, we gain not just a window into the past, but also a deeper appreciation for the complexity and mystery of the universe itself. As scientists continue to explore these cosmic puzzles, they are inching ever closer to unveiling the secrets of our existence, from the smallest fluctuations in temperature to the grandest questions about the fabric of reality. The cosmic microwave background, CMB, serves as more than just a faint afterglow of the Big Bang. It is a monumental key to unraveling the very origins of the universe. This pervasive radiation, often referred to as the oldest light in the universe, is not merely a relic of the past, but a detailed blueprint etched into the fabric of space-time. It holds the imprints of the early universe, reflecting both the moments immediately after the Big Bang and the intricate processes that led to the formation of galaxies, clusters, and other large-scale structures. In its essence, the CMB is a snapshot of the universe when it was just a few 100,000 years old. During this time, the universe transitioned from a hot, dense state to one where atoms formed for the first time. This process allowed photons to travel freely, giving birth to the radiation we now observe as the CMB. However, this radiation is far from uniform. It carries tiny temperature fluctuations, each variation acting as a crucial piece of the puzzle that tells the story of cosmic evolution. Interestingly, these fluctuations are not random. They follow distinct patterns and scales of density variation that help set the initial conditions for the vast cosmic structures we observe today. These density variations, which varied in amplitude, were responsible for determining the regions in space where galaxies would eventually form and cluster together. In this way, the backdrop of the CMB is much more than just a relic. It is the foundational blueprint for the universe's architecture. As scientists delve deeper into the CMB, it becomes clear that this ancient light offers a powerful means to probe the cosmos. By analyzing its fluctuations, astronomers can learn about the age, composition, and evolution of the universe itself. These minute variations in temperature and density map out the invisible cosmic web, which eventually coalesced into the galaxies and stars that populate the universe. The intricate relationship between these fluctuations and galaxy formation demonstrates the dynamic and ongoing interaction between cosmic radiation and the large-scale structure of the universe, unveiling the origins of our galaxy clusters and their continuous development. When the CMB was first identified in the 1960s by scientists Arno Penzias and Robert Wilson, it was considered a crucial piece of evidence supporting the Big Bang theory. The discovery of this faint glow emanating from every corner of the universe was an important step in confirming that the universe had once been in an intensely hot and dense state before it began expanding and cooling. In those early days of discovery, the CMB was largely regarded as a remnant of the Big Bang, a passive signal that had little to offer beyond confirming the universe's explosive origins. However, as technology advanced, particularly with the launch of missions such as the Cosmic Background Explorer, COBE, in the 1980s, our understanding of the CMB evolved. Detailed measurements of the temperature fluctuations in the CMB revealed subtle variations in density, offering the first clues about the early universe's structure. These fluctuations acted like a cosmic fingerprint, showing where matter was more densely packed and where it was sparse. This imprint from the early universe would eventually evolve into the complex, interconnected cosmic structures we see today: galaxies, clusters of galaxies, and the large-scale cosmic web. Further advancements in observational technology, such as the deployment of the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, allowed cosmologists to take a more refined approach to interpreting CMB data. These missions provided a much clearer picture of the early universe's conditions. The results offered valuable insights into key cosmological parameters, such as the rate of expansion of the universe, the density of dark matter, and the enigmatic nature of dark energy. Through these observations, scientists were able to determine that approximately 70% of the universe is made up of dark energy, an elusive force driving the accelerated expansion of the cosmos. This discovery has dramatically reshaped our view of the universe. No longer seen as a static and unchanging backdrop, the universe is now understood as a dynamic, evolving entity, continually shaped by unseen forces, such as dark matter and dark energy. The CMB has become far more than just a remnant of the Big Bang. It is a vital tool for probing the fundamental building blocks of the universe. As each new discovery related to the CMB is made, our understanding of the cosmos becomes more intricate, leading us closer to unraveling the mysteries of space-time, matter, and energy. Today, the study of the CMB involves a sophisticated array of tools and methods designed to extract the most information possible from this faint afterglow. One of the primary instruments used in this analysis is the microwave detector, which is capable of precisely measuring the radiation emitted by the CMB. These detectors are often arranged in large arrays, allowing scientists to capture data from vast sections of the sky and build up a panoramic view of the universe's background radiation. Satellite observatories such as WMAP and Planck have become crucial in the study of the CMB, as they operate above the Earth's atmosphere, free from the distortions caused by atmospheric interference. These high-altitude instruments can capture highly detailed measurements of temperature fluctuations, offering key insights into the conditions of the early universe. The data collected by these spacecraft is then processed using complex algorithms and statistical models, such as harmonic analysis, to isolate and interpret the subtle variations in temperature and polarization of the CMB. This analysis helps scientists understand the distribution of matter and energy in the early universe, shedding light on the formation of galaxies and the overall structure of the cosmos. Furthermore, computer simulations are frequently employed to compare the observed CMB data with theoretical models. By simulating the physics of the early universe, researchers can predict how the CMB would appear under various conditions. This comparison between observed data and simulated models helps scientists refine their understanding of fundamental concepts such as dark matter, dark energy, and the very structure of the universe itself. In this way, the CMB acts as both a mirror to the past and a guide to the future of cosmological research. The temperature fluctuations in the CMB are perhaps the most important aspect of this radiation. These slight variations, often no more than 1 part in 100,000, are the signatures of density fluctuations in the early universe. They are the cosmic seeds that grew into the galaxies, stars, and clusters that populate the universe today. By studying these fluctuations, scientists can learn about the amount and distribution of ordinary matter, and dark energy present in the universe. For example, the density of dark matter, which cannot be directly observed since it does not emit light, can be inferred by studying the gravitational effects it had on the early universe's fluctuations. Beyond mapping out the presence of dark matter, the CMB also offers critical insights into dark energy, the mysterious force responsible for the universe's accelerated expansion. By analyzing the geometry of the universe revealed through CMB measurements, scientists can estimate the amount of dark energy present. The CMB has thus become a tool for refining cosmological models and understanding the complex roles of both dark matter and dark energy in shaping the universe's evolution. In recent years, advances in technology, including the high-precision measurements from the Planck satellite, have provided more accurate data on the CMB. These improvements have enabled scientists to better understand dark matter and dark energy, offering us a clearer picture of these unseen forces and their profound influence on the universe. As our measurements become more refined, the interplay between the CMB, dark matter, and dark energy continues to deepen our understanding of the universe's past, present, and future. In conclusion, the cosmic microwave background is not merely a faint echo of the Big Bang, but a treasure trove of information about the universe's earliest moments. Through careful analysis of its temperature fluctuations and polarization patterns, we can trace the formation of galaxies, the distribution of dark matter, and the evolution of the universe itself. Each new breakthrough in the study of the CMB brings us closer to answering the most profound questions about the cosmos, and the journey of discovery continues to unfold. The cosmic journey, a vast expanse of wonder and discovery, has been profoundly shaped by meticulous measurements that have allowed scientists to refine our understanding of the universe. Among the most pivotal breakthroughs in modern cosmology is the determination of the amounts of dark matter and dark energy, two of the most mysterious and yet essential components of the cosmos. These measurements have not only provided a deeper insight into the universe's makeup, but have also illuminated the path for understanding its expansive evolution and eventual fate. By observing subtle patterns and statistical distributions of fluctuations within the cosmic microwave background, CMB, researchers have established a foundational framework for understanding the universe's expansion, a process that continues to be a cornerstone in cosmological models. This growing precision has reinforced key aspects of the theory of cosmic inflation. Inflation suggests that in the earliest moments after the Big Bang, the universe underwent an explosive period of rapid expansion. The exploration of temperature fluctuations in the CMB has also underscored the critical role of advanced technology in cosmology. Missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck spacecraft have revolutionized our view of the universe by providing incredibly detailed maps of these temperature differences, allowing us to better grasp the underlying principles of cosmological phenomena. As researchers continue to analyze these data, they push the boundaries of our knowledge, uncovering new insights into the origins and evolution of the cosmos. Current research is intensely focused on resolving the lingering questions regarding anomalies within the CMB. These anomalies, observed as irregularities in the cosmic background radiation, present both a challenge and an opportunity. They may indicate a fundamental shift in our understanding of the universe's structure, or they could simply be statistical outliers, irrelevant to the broader cosmological picture. To address these mysteries, researchers are employing cutting-edge observational tools. Satellite missions and ground-based telescopes are helping refine measurements of the CMB, which is essentially the afterglow of the Big Bang. With greater precision, scientists can now probe the subtle variations in temperature and polarization across the sky, providing invaluable data that is essential for understanding the anomalies that have been previously identified. For example, the Planck satellite, which has produced some of the most comprehensive maps of the CMB, is continuously reanalyzed to extract the maximum amount of information. These reanalyses are crucial for uncovering insights that earlier studies may have overlooked. Theoretical physicists, meanwhile, are exploring a variety of models to explain the anomalies. Some are considering modifications to the inflation theory, while others are delving into the possibility of unknown phenomena, such as primordial non-Gaussianities or cosmic topological defects. These alternative cosmological scenarios could either deepen our understanding of the universe or prompt a complete reevaluation of the framework upon which current models are built. The interplay between theorists and observational astronomers is particularly dynamic, fostering a collaborative environment in which new hypotheses are rigorously tested against the latest data. This collaboration also extends to the use of computer simulations, which visualize and predict the formation of microstructures in the universe. These simulations not only help inform observational priorities, but also provide a broader context for interpreting the data in new and exciting ways. As these multifaceted research efforts continue, they promise to uncover more than just answers to specific anomalies in the CMB. They will deepen humanity's understanding of the universe's grand, intricate tapestry. In recent decades, astronomers have uncovered compelling evidence for the accelerating expansion of the universe, a phenomenon that radically reshapes our conception of the cosmos. This discovery came to light in the late 20th century through the study of distant supernovae, particularly a specific type known as Type 1a supernovae. These stellar explosions, which mark the dramatic end of a star's life cycle, have proven to be essential tools in measuring cosmic distances. When scientists first observed these supernovae, they expected to see a consistent deceleration in the universe's expansion. Instead, the data revealed something entirely unexpected. The supernovae were fainter than anticipated, suggesting that they were farther away than originally thought. This indicated that the universe was not slowing down as expected, but accelerating. The significance of this discovery became clear when two independent research teams published their findings in 1998, ultimately leading to the groundbreaking conclusion that some unknown force was driving this accelerated expansion. This force, later termed dark energy, is thought to account for approximately 70% of the universe's total energy density, though its exact nature remains one of the greatest mysteries in modern physics. The term dark doesn't imply mere invisibility, but rather highlights the fact that scientists have yet to determine its properties or how it interacts with other known forces in nature. Evidence for dark energy and the universe's accelerating expansion is further corroborated by observations of the CMB and large-scale cosmic structures. The discovery that the universe is not only expanding, but doing so at an accelerating rate has fundamentally altered our understanding of cosmology. It has prompted profound questions about the future of the universe, its ultimate fate, and the role dark energy plays in the ongoing evolution of cosmic structures. This evolving perspective invites humanity to dive deeper into the cosmos, seeking answers to the profound mysteries of dark energy and its impact on the universe's expansion. Type Ia supernova, in particular, have become instrumental in this exploration. These explosions occur when a white dwarf star accumulates matter from a companion star, eventually reaching a critical threshold that leads to a cataclysmic detonation. Because Type 1a supernovae exhibit a consistent peak brightness, they serve as standard candles for measuring astronomical distances. By observing these supernovae in distant galaxies, astronomers can calculate their distance based on their brightness. When this distance information is combined with redshift data, indicating how much the universe has expanded since the light left the supernova, a relationship emerges between distance and the speed of recession. Essentially, the further away a galaxy is, the faster it appears to be moving away from us, a phenomenon confirmed by the light emitted by supernovae acting as beacons across the cosmos. The most groundbreaking moment came in the late 1990s when two independent teams of astrophysicists used Type Ia supernovae to probe the rate of cosmic expansion. They not only confirmed that the universe was expanding, but also revealed that this expansion was accelerating. This startling discovery led to the hypothesis that an unknown form of energy, dark energy, was responsible for driving this acceleration. Supernovae, therefore, have become pivotal in shaping our understanding of the dynamics of the universe. They provide crucial clues that help us grasp the delicate balance of forces at play in cosmic evolution, especially in the interplay between gravity and the mysterious force accelerating the universe's expansion. While dark energy remains the leading explanation for cosmic acceleration, alternative theories also continue to emerge. One such theory involves modifications to the laws of gravity, as formulated by Albert Einstein. According to the theory of generalized Einstein gravity, additional terms could be added to Einstein's equations, altering gravitational interactions at vast cosmic scales. Another theory proposes the existence of extra dimensions, as suggested by various theoretical frameworks, including string theory. In this view, our universe could contain more dimensions than the familiar three of space and one of time. If true, these extra dimensions could exert an influence on gravitational forces, potentially contributing to the accelerated expansion. Additionally, the concept of a cosmic scalar field, known as quintessence, offers another intriguing explanation. Unlike the constant energy density assumed in models of dark energy, quintessence posits that the energy density of the universe changes over time as the scalar field evolves. This dynamic model introduces an adjustable factor, allowing it to accommodate a range of observational data and offering an alternative perspective on the cosmic acceleration. As research progresses, each of these theories will be tested and refined, pushing the boundaries of our understanding of the universe and its mysterious forces. The discovery of cosmic acceleration has opened a new chapter in cosmology, one that challenges our fundamental assumptions and invites us to explore the deepest questions about the nature of the cosmos itself. Some scientists examine the nature of gravitational interactions on large cosmological scales in a way that differs significantly from how they approach them locally. This idea draws from alternative theories such as the Dali-Gabad-Parati model, which proposes that our universe could be a three-dimensional brain embedded within a higher dimensional space. In such a framework, gravity's effects might vary with distance, causing cosmic expansion to behave in unexpected, complex ways. This challenges the traditional view that gravity's influence is uniform throughout the universe. Before the early 20th century, many scientists adhered to the concept of a static, unchanging universe. Pioneers like Albert Einstein believed the cosmos was eternal and unaltered by time. To support this idea, Einstein formulated his general theory of relativity and introduced the cosmological constant, a term in his equations designed to counteract the force of gravity, preventing it from causing the universe to collapse upon itself. However, this perception underwent a dramatic shift in the 1920s, when astronomers began detailed observations of the universe. The groundbreaking work of Edwin Hubble marked a turning point. In a series of revolutionary discoveries, Hubble revealed that distant galaxies were moving away from us. This observation signified that the universe was not static, as previously thought, but was instead expanding. Hubble's data also unveiled a direct relationship between a galaxy's distance from Earth and its redshift. Redshift occurs when the light from an object moving away from an observer is stretched, shifting its wavelengths toward the red end of the spectrum. In simpler terms, the farther away a galaxy is, the faster it is receding. This observation shattered the long-held belief of a stable, unchanging cosmos. The discovery of cosmic expansion pointed to a more profound conclusion. The universe had a beginning. This notion became central to the development of the Big Bang theory, which proposes that the universe originated from an incredibly hot, dense state and has been expanding ever since. This revelation fundamentally altered our understanding of the universe, indicating not only that it was dynamic and evolving, but also that it had a beginning, challenging the idea of a timeless, static backdrop. As this new view of the universe unfolded, scientists began to explore the deeper implications of cosmic expansion. One of the most perplexing and fascinating of these is the nature of dark energy, an enigmatic force driving the accelerated expansion of the universe. This mysterious energy accounts for approximately 70% of the total energy content of the universe, yet its properties remain largely unknown. What exactly is dark energy? How does it work? And what will be its role in the far future? The accelerated expansion of the universe means that not only is space expanding, but it is doing so at an ever-increasing rate. As the universe stretches, galaxies are gradually moving further apart, and eventually they will drift beyond the observable horizon. This poses a future where distant galaxies recede so rapidly that their light will no longer be visible from Earth, leaving the cosmos increasingly dark and cold. Over trillions of years, stars will burn out, galaxies will fade into obscurity, and the remaining matter will become increasingly sparse. In this distant future, the universe may enter a state known as the Big Freeze, where it reaches maximum entropy, essentially the point at which all available energy is evenly distributed, and no processes that require energy can take place. In this scenario, life as we know it would become impossible, as the universe's resources would dwindle and galaxies would be scattered far apart. The end result might be a nearly empty, frozen cosmos, with only dark remnants of stars and black holes left behind. However, another possible fate of the universe, though more speculative, is the concept of the Big Rip. In this scenario, if dark energy's influence continues to grow stronger over time, it could eventually overpower the gravitational forces holding galaxies, stars, planets, and even atoms together. Such an outcome would result in the universe being torn apart at every level, from the largest cosmic structures to the very fabric of matter itself. This dramatic fate underscores how much we still have to learn about the fundamental forces and the underlying principles governing the cosmos. The exploration of these profound possibilities is not only reshaping our understanding of the universe's evolution, but also pushing us to reconsider our place in an ever-changing cosmos. To delve deeper into the nature of cosmic expansion and its ultimate consequences, scientists have developed a range of innovative methods to simulate and study these processes. One of the most powerful tools in cosmology involves computer simulations that model the behavior of galaxies and other cosmic structures over vast timescales. These simulations employ sophisticated algorithms designed to replicate the effects of dark matter, dark energy, and gravitational forces. By manipulating different variables, scientists can observe how cosmic expansion influences the formation and evolution of galaxies, offering a virtual glimpse into the universe's past, present, and potential future. Another approach involves analog experiments where scientists create controlled models of cosmic conditions in laboratory settings. For example, researchers can use fluids and lasers to mimic the expansion of space. In these experiments, wave patterns in the fluid behave in ways that replicate the stretching of light caused by the universe's expansion. Such analog systems help scientists explore critical phenomena, such as the cosmic inflation that occurred shortly after the Big Bang, offering insights into the earliest moments of the universe. In addition to computer simulations and laboratory experiments, researchers also investigate the principles of general relativity and their effects on space-time. By studying how mass and energy influence the curvature of space-time under different conditions, scientists gain a deeper understanding of how gravity interacts with cosmic expansion. These experiments not only help us understand the past and present state of the universe, but also allow us to test hypotheses about its ultimate fate. Through these diverse methods, scientists are piecing together the complex puzzle of cosmic expansion. Each breakthrough, whether a new simulation, experimental discovery, or theoretical insight, brings us one step closer to grasping the grand, sweeping history of the cosmos and our place within it. At the core of this research lies the ongoing mystery of dark energy. Despite its central role in driving the accelerated expansion of the universe, dark energy remains elusive. What is it made of? Does it remain constant, or does its influence evolve over time? Various theories attempt to explain its properties, from Einstein's original concept of the cosmological constant to more speculative ideas that involve modifications to gravity or entirely new physical laws that we have yet to uncover. The quest to understand dark energy and its impact on the cosmos continues to be one of the most exciting and profound areas of scientific inquiry, with the potential to reshape our entire understanding of the universe's future. In the end, our search for answers about the cosmos is not just an intellectual exercise, but a journey into the unknown, a journey that continually challenges our perceptions of space, time, and the very nature of reality itself. Gravity, a force so fundamental to our understanding of the cosmos, plays a pivotal role in the grand cosmic puzzle. It is this very force that seeks to draw matter together, an effect that under normal circumstances, would serve to slow down the universe's expansion. However, when we observe the cosmos, a striking contradiction emerges. Instead of decelerating, galaxies are moving away from each other at an ever-accelerating rate. This perplexing discovery challenges our conventional understanding and raises profound questions. Are our current models of gravity truly complete? Or do we need to introduce new concepts to account for the enigmatic forces shaping cosmic behavior? The quest to answer these questions may lie in the development of a unified theory, one that marries the principles of quantum mechanics with the framework of general relativity. This theory could offer a comprehensive understanding of the forces that govern the universe. As astronomers push the boundaries of technology, peering deeper into the vast expanse of space with increasingly advanced instruments, from high-powered telescopes to deep space probes, they continue to refine and expand our knowledge of the universe's most elusive phenomena. With each new discovery, fresh questions arise, prompting a shift in our understanding and sparking curiosity about the unexplored frontiers of the cosmos. In this pursuit, gravitational waves offer an unprecedented opportunity to probe the universe. These ripples in the fabric of space-time, generated by cataclysmic events such as the collision of black holes or neutron stars, travel across the cosmos at the speed of light. When these colossal celestial bodies merge, they send out waves that reverberate through space-time, carrying information not only about the objects that created them, but also about the very nature of the universe itself. The detection of gravitational waves allows scientists to observe phenomena that are otherwise invisible, providing a clearer picture of cosmic events and offering a unique way to explore the evolution of the universe. Gravitational waves become particularly intriguing when viewed in the context of the universe's expansion, a concept first proposed in the early 20th century. As the universe grows, distant galaxies recede from us, causing the light emitted by these galaxies to stretch, a phenomenon known as redshift. Traditional observations, which primarily focus on electromagnetic radiation, are limited by the interference of cosmic dust, gas, and other obstructions that can obscure the light. In contrast, gravitational waves offer a means to study the universe unaffected by these obstacles, providing a clearer, unobstructed view. By combining gravitational wave data with conventional astronomical observations, scientists gain a more comprehensive understanding of cosmic events. For instance, the detection of a gravitational wave event, accompanied by the electromagnetic signals from a gamma-ray burst, has opened new avenues for understanding both the merging of these celestial bodies and the rate at which the universe is expanding. This multi-messenger approach, which integrates multiple types of data, allows researchers to gain a fuller perspective on cosmic dynamics, enriching our grasp of the underlying physics driving these events. As researchers continue to refine gravitational wave detectors and extend their reach across the cosmos, these insights may eventually shed light on one of the universe's greatest mysteries: dark energy. This enigmatic force is believed to be driving the accelerated expansion of the universe, but its true nature remains elusive. By studying the relationship between gravitational waves and the universe's expansion, scientists hope to uncover more about this elusive force and its role in the evolution of the cosmos. This research is not just an intellectual pursuit, but a crucial step in answering profound questions about our place in the universe. The expansion of the universe is primarily described by a set of equations derived from Albert Einstein's general theory of relativity. At the heart of this framework is the Friedmann-Lemaître-Robertson-Walker FLRW metric, a mathematical formulation that serves as a foundation for understanding the universe's expansion over time. This model assumes a homogeneous and isotropic universe, meaning that on a large scale, the universe appears the same, regardless of where you are or in which direction you look. From the FLRW metric, the Friedmann equations are derived, and these equations detail how the universe's scale factor changes over time. The scale factor is a function that describes how distances between objects in the universe expand or contract as time progresses. The first Friedmann equation links this scale factor to the energy density of various components of the universe, including matter, radiation, and dark energy. This equation highlights the contributions of both ordinary and dark matter to the expansion of the universe, revealing how these elements interact to shape cosmic dynamics. In addition, the second Friedmann equation incorporates the pressure of the universe's content, offering a more complete picture of how different forms of energy behave under cosmic conditions. This includes the repulsive effect of dark energy, which is thought to be the primary force responsible for the accelerated expansion of the universe in the present day. To visualize this, imagine inflating a balloon. As the balloon expands, any 2 points on its surface move further apart. Similarly, in the universe, space itself is stretching, causing galaxies that were once relatively close to one another to drift farther apart as the universe expands. These equations provide a mathematical framework for understanding not only the past history of the universe, but also its future trajectory. By studying the expansion through these complex models, scientists gain insights into the ultimate fate of the cosmos, helping us to understand whether the universe will continue to expand forever, or if other forces will eventually bring about its collapse. As the universe expands, this stretching of space has a profound effect on our observations of distant galaxies. When light travels across vast distances in space, the stretching of space causes the wavelengths of that light to elongate, a phenomenon known as redshift. As light from distant galaxies reaches us, its wavelengths become stretched, shifting toward the red end of the spectrum. This redshift serves as a crucial tool for astronomers, allowing them to measure not only the speed at which galaxies are receding from us, but also the rate at which the universe itself is expanding. Moreover, when we observe distant galaxies, we are essentially looking back in time. The light that reaches us from these galaxies has traveled for billions of years, meaning we are seeing them as they were in the past, not as they are today. This time travel aspect allows astronomers to piece together the history of galaxy formation and evolution, offering a glimpse into the early stages of the universe's development. However, as the universe continues to expand, the distances between galaxies grow, making it increasingly difficult to measure their current positions and properties. The farther away a galaxy is, the faster it appears to be receding from us. This raises important questions. Do the measurements we obtain accurately reflect the current state of these galaxies, or are they a snapshot of the universe as it was billions of years ago? Dark energy adds another layer of complexity to this issue. As the primary force driving the accelerated expansion of the universe, dark energy not only speeds up cosmic expansion, but also complicates our measurements of distant objects. The influence of dark energy means that the distances we measure using standard candles, like supernovae, may not match earlier theoretical predictions, leading to potential revisions of our cosmological models and a deeper investigation into the nature of this mysterious force. The expansion of the universe also affects the cosmic microwave background radiation, CMB, the afterglow of the Big Bang. As the universe expands, this ancient radiation stretches, shifting toward longer wavelengths. By studying these changes, scientists can refine their models of the universe's early evolution and gain new insights into its past. The CMB serves as a snapshot of the universe in its infancy, and by analyzing its shifts, we can gain a deeper understanding of the forces that have shaped the cosmos. The interplay between expansion, redshift, and dark energy remains one of the most fascinating areas of contemporary research. The universe, it seems, is not a static entity, but a dynamic and ever-evolving one, with forces at play that we are still striving to fully comprehend. Today, astronomers face several daunting challenges as they continue their quest to unlock the universe's most profound mysteries. One of the most significant obstacles is the sheer vastness of the universe. The distances involved are so immense that gathering direct observations can be exceedingly difficult. For instance, when studying galaxies billions of light years away, the light or signals we receive today were emitted long before humanity even existed. This means that astronomers are often looking into the distant past, which complicates the interpretation of more recent cosmic phenomena. Another challenge lies in the sheer volume of data generated by modern observational technology. Telescopes and space probes now collect data across a wide spectrum of wavelengths, from radio waves to gamma rays. The sheer quantity of this data can be overwhelming, and processing it requires not just advanced algorithms, but also significant computing power. As astronomers sift through countless signals, the task of identifying meaningful, groundbreaking discoveries becomes increasingly complex, requiring both technological innovation and intellectual perseverance. In the end, the search for answers to the universe's most fundamental questions is a continuous process, one that is shaped by the constant evolution of both our understanding and our technology. The more we learn, the more questions arise, and the more deeply we are drawn into the mysteries of the cosmos. Cosmic phenomena remain one of the greatest frontiers of human understanding, with many aspects still clouded in mystery. While we have made tremendous strides in exploring the vastness of space, there are still a number of phenomena that continue to elude our grasp. Take, for instance, dark matter, a substance that, despite accounting for roughly 27% of the universe's total mass and energy, remains invisible to our most advanced instruments. We know it must exist due to its gravitational effects on galaxies, but we have yet to directly observe it. Numerous theories attempt to explain its nature, yet without solid evidence, these remain speculative, leaving us in a state of uncertainty. Similarly, dark energy, black holes, and the very nature of cosmic inflation continue to present immense challenges to modern science. These topics, each rich with unanswered questions, form the backbone of cosmology's most puzzling phenomena. Scientists are faced with a paradox. Despite the incredible progress in our understanding of space, the more we discover, the more questions seem to arise. This paradox underscores the complexity of the universe, with its myriad forces and objects that defy conventional understanding. In order to unlock these secrets, a key factor is the financial and collaborative resources necessary to drive the research. The study of the cosmos often requires massive international cooperation. Astronomers and physicists frequently rely on partnerships across nations to pool expertise, technology, and funding. However, securing the necessary financial support for such large-scale endeavors remains a continuous challenge. As the demands for more powerful telescopes, satellites, and other advanced instruments increase, prioritizing which projects receive funding becomes a crucial aspect of space exploration. In this environment, it is clear that overcoming these financial hurdles is essential for advancing our collective understanding of the universe. Despite these challenges, the ongoing collaboration between nations continues to fuel the quest for cosmic knowledge. The joint efforts of institutions around the world foster breakthroughs that might otherwise be impossible if research remained confined to individual nations. One of the most remarkable examples of this is the Event Horizon Telescope, which in 2019 captured the first ever image of a black hole. This monumental achievement would not have been possible without the collaboration of scientists from across the globe. By connecting radio telescopes located in various parts of the world, the team was able to combine their data and achieve a level of detail never before seen in the study of black holes. International collaborations like these are also vital in providing the necessary resources to build and maintain the state-of-the-art research infrastructure required for such complex investigations. Observatories situated in remote locations, free from the interference of light pollution and other urban disturbances, rely on these global partnerships for financial backing and technological support. These facilities offer unprecedented opportunities for astronomers to study the universe in a way that would be impossible without international investment. The pooling of financial and technological resources does more than just enable the construction of advanced equipment. It accelerates the pace of discovery. By sharing resources, countries can push the boundaries of research without being hindered by individual constraints. Moreover, these collaborations often result in a dynamic exchange of ideas, methodologies, and scientific perspectives, enriching the global scientific community as a whole. Researchers can learn from each other's unique approaches and techniques, which leads to the development of new and innovative methods to tackle long-standing cosmic questions, such as the nature of dark matter and the expansion of the universe. Perhaps most importantly, the spirit of collaboration highlights the shared curiosity of humanity. Regardless of national origin, the collective effort to understand the cosmos underscores the fact that our quest for knowledge transcends borders and divisions. It speaks to our universal desire to understand the universe and our place within it. While international collaboration plays a crucial role in the study of space, the contributions of everyday citizens have become increasingly valuable in unraveling the mysteries of the cosmos. Citizen science, where members of the public engage in scientific research, has proven to be an indispensable tool in advancing our knowledge. By tapping into the collective intelligence of ordinary people, researchers are able to tackle problems that may have been too large or too complex for a small group of scientists to address alone. This grassroots approach brings fresh perspectives and diverse skill sets to the table, often leading to novel solutions to long-standing questions. One of the most remarkable examples of citizen science is the project Galaxy Zoo. This initiative invites volunteers from around the world to help classify galaxies based on their shape, structure, and other characteristics. The task of sifting through vast amounts of astronomical data would be overwhelming for a small team of professionals, but through the collective efforts of thousands of volunteers, the process becomes far more manageable. This collaboration has not only sped up the classification of galaxies, but also led to the discovery of previously unknown types of galaxies, providing invaluable insights into the formation and evolution of the universe. In addition to classifying galaxies, citizen scientists have also played a critical role in the detection of exoplanets, planets located outside our solar system. Projects such as Planet Hunters allow amateurs to analyze light curves from distant stars, searching for the subtle dips in brightness that indicate the presence of a planet passing in front of its host star. This task, which requires analyzing vast amounts of data, would be virtually impossible without the involvement of a large number of volunteers. As a result, citizen scientists have contributed to the discovery of numerous exoplanets, expanding our understanding of how common planetary systems may be across the galaxy. In both the classification of galaxies and the search for exoplanets, citizen science demonstrates the power of collective effort. By involving the public in the scientific process, researchers can increase the scale and efficiency of their investigations while also fostering a deeper connection between society and the universe. Through this collaboration, we gain new insights into the fundamental questions of existence, such as the potential for life on other worlds and the structure of the universe itself. Ultimately, the continued pursuit of knowledge about the cosmos requires both scientific expertise and the support of an engaged global community. As we look to the future, The challenges we face in understanding space will undoubtedly become more complex, but so too will the solutions. With the combined efforts of international collaborations, citizen scientists, and dedicated researchers, the mysteries of the universe will continue to unfold, one discovery at a time. Citizen science has become a cornerstone in the exploration of space, playing an indispensable role in monitoring space weather and furthering our understanding of complex cosmic phenomena such as gamma-ray bursts and gravitational waves. Through the collaboration of dedicated individuals with scientific institutions, the public can now actively contribute to the analysis of vast data streams from observatories and satellites across the globe. These contributions not only help predict and respond to explosive cosmic events, but also push the boundaries of discovery. This joint effort between amateur enthusiasts and professional scientists has revealed how the curiosity and passion of the public can lead to breakthroughs in our understanding of the universe. It exemplifies the power of citizen participation in science, where the quest for knowledge becomes a shared and communal journey. One of the most significant tools in this journey is the network of space telescopes and observatories, which have revolutionized how we study the cosmos. These instruments, stationed far beyond Earth's atmosphere, allow astronomers to peer into the universe without the interference caused by the planet's atmospheric distortions. Earth's atmosphere distorts and absorbs light, and it limits observations to a narrow range of wavelengths. However, by positioning telescopes in space, scientists gain an unobstructed view of celestial objects, accessing information from various spectrums, including ultraviolet, X-ray, and infrared light. Among the most renowned space telescopes, the Hubble Space Telescope stands out. Since its launch in 1990, Hubble has been instrumental in transforming our understanding of distant galaxies, nebulae, and exoplanets. With its capability to capture high-resolution images, Hubble has not only provided breathtaking visuals, but also invaluable data that have allowed scientists to track the expansion rate of the universe. It has also offered insights into stellar evolution, revealing the processes that govern the birth, life, and death of stars. As our knowledge deepens, we understand the intricate life cycles of these stellar bodies in greater detail. Meanwhile, the James Webb Space Telescope, launched much more recently, has begun to peel back the mysteries of the early universe. By detecting faint infrared light emitted by the first stars and galaxies, Webb is enabling scientists to unravel the origins of cosmic structures. It has provided unprecedented insights into the transition from a dark, featureless universe to one brimming with stars and galaxies. This telescope is allowing us to trace the very first moments in the universe's history and watch the cosmic dawn unfold. Beyond capturing images, space observatories also play an essential role in data gathering through spectrometry. This technique enables astronomers to analyze the composition and movement of celestial bodies, offering breakthroughs in our understanding of the universe. From identifying the elemental makeup of stars to examining the atmospheres of exoplanets, spectrometry has expanded our knowledge of fundamental cosmic processes. Furthermore, it aids in investigating some of the most enigmatic aspects of the universe, including dark matter and dark energy, whose very existence continues to puzzle scientists. The rapid advancements in technology and observational techniques continue to push the limits of human understanding, like revealing a universe far more complex and expansive than we ever imagined. In the ever-evolving field of astronomy, artificial intelligence has emerged as a pivotal partner. With the explosion of data produced by telescopes and satellites, astronomers are increasingly relying on AI to sift through and interpret vast data sets. The sheer scale of data, from high-resolution images of faraway galaxies to recordings of transient cosmic events, often exceeds what human researchers can handle manually in a practical time frame. AI steps in to simplify this challenge, transforming an otherwise overwhelming task into a more manageable and insightful process. One of the most valuable applications of AI in astronomy is its role in pattern recognition. Machine learning algorithms can be trained to identify and classify various celestial phenomena, from supernovae to exoplanets and even potential gravitational waves. AI can, for example, analyze the light curves of stars to detect planets transiting in front of them. This automated process accelerates discoveries and increases the accuracy of identifying potentially habitable exoplanets. By recognizing patterns and making precise predictions, AI speeds up the discovery process, allowing scientists to uncover new worlds faster than ever before. AI also holds tremendous promise in solving some of the universe's greatest unsolved mysteries. Take, for instance, the elusive nature of dark matter and dark energy. By analyzing the data gathered from cosmic surveys, AI can help identify subtle inconsistencies that may offer crucial clues about these mysterious components of the cosmos. In this way, AI can process and model vast amounts of data, testing competing theories and inching us closer to understanding the fundamental forces that govern our universe. As AI technology evolves, its potential to revolutionize astronomy grows, creating new paths to understanding and unraveling the universe's most complex phenomena. Looking to the future, the horizon is filled with exciting missions designed to uncover even more of the cosmos's secrets. One such mission is the upcoming European Space Agency's Euclid mission, set to launch in the next few years. Euclid will focus on mapping the three-dimensional distribution of dark energy and dark matter throughout the universe. While this mission's primary aim is to study these enigmatic cosmic components, its powerful imaging and spectroscopic tools may also provide crucial data on rogue planets, those that have been ejected from their parent stars and wander through space without a gravitational anchor. The insights gained could help scientists understand the origins and characteristics of these mysterious objects. In addition to Euclid, the NASA Wide Field Infrared Survey Telescope, WF-IRST, anticipated to launch in the mid-2020s, will provide invaluable data on exoplanets. By observing the infrared spectrum, WF-IRST will help astronomers explore exoplanets that exist outside the typical habitable zones of stars. Its wide field of view will also make it well-suited to detect rogue planets drifting through the galaxy. By studying the atmospheres and compositions of these planets, WF-IRST could answer fundamental questions about the formation and evolution of planetary systems. On the ground, observatories such as the Vera C. Rubin Observatory in Chile are also gearing up for their own set of groundbreaking discoveries. With its unparalleled survey capabilities, the observatory's Legacy Survey of Space and Time will conduct a comprehensive mapping of the southern sky. This ambitious project could lead to the discovery of objects that wander the galaxy without being bound to any particular star, further enriching our understanding of planetary demographics. These missions, whether in space or on the ground, hold immense potential for revealing the hidden aspects of the universe, including the rogue planets that have long intrigued astronomers. As technology continues to advance and observational strategies improve, the data gathered will undoubtedly shed new light on the enigmatic nature of these celestial objects, deepening our understanding of their role in the broader cosmic landscape. At the core of much of this work are theoretical models, which serve as frameworks to interpret observational data. These models are essential for making sense of the universe's complexities. When astronomers observe a distant galaxy or a cosmic event, they gather data that can often be interpreted in multiple ways. Theoretical models provide predictions based on physical laws, helping to clarify these observations. For example, the light we receive from a distant galaxy can reveal its chemical composition and the movement of its stars. By analyzing the galaxy's redshift, the shift of its light toward the red end of the spectrum, we can deduce whether it is moving away from us, offering insights into the expansion of the universe. Moreover, theoretical models can predict phenomena that have yet to be observed. For instance, the theory of cosmic inflation helps explain the distribution of galaxies and the background radiation that fills the universe. These models propose that certain conditions in the early universe led to the observed large-scale structure of the cosmos. They guide future observations and allow astronomers to refine their instruments and target specific celestial events, such as gravitational waves or the merging of black holes. Thus, theoretical models not only help interpret existing data, but also inspire the next steps in humanity's quest to explore the mysteries of the universe. Theoretical models play an essential role in modern astrophysics, providing a powerful tool for simulating scenarios that would otherwise remain beyond our reach due to limited or incomplete real-world data. For instance, phenomena such as the environments inside black holes or the intricate processes during the formation of stars are incredibly challenging to observe directly. Yet, through these models, scientists can explore these otherwise inaccessible realms. By running countless simulations, tweaking variables, and testing different conditions, researchers gain invaluable insights into how fundamental forces, such as gravity and nuclear interactions, shape the cosmos in ways that would be impossible to discern from observation alone. This dynamic interaction between observational data and theoretical models is a continuous, evolving process. Observations often serve as a reality check, refining existing theories or even sparking new questions that push our understanding further. In turn, theoretical models adapt to incorporate these new insights, providing a robust framework for ongoing exploration. This symbiotic relationship between theory and observation ensures that as we gaze into the stars, we are not merely collecting data, but are also equipped with conceptual tools to interpret the underlying mechanisms that drive the universe's grand design. Unlocking the mysteries of the universe requires a multifaceted, interdisciplinary approach. Astrophysics does not operate in isolation. It draws heavily on insights from other scientific fields to confront the vast unknowns that exist in the cosmos. Physics, both classical and quantum, is foundational, explaining phenomena from black holes to dark matter. The fusion of these principles with advanced mathematics has led to the development of increasingly sophisticated models that describe the universe's structure and behavior in intricate detail. The synergy of physics and mathematics, however, is not the whole story. In recent decades, partnerships between astrophysics and computer science have revolutionized our ability to process and analyze vast amounts of astronomical data. With the aid of powerful algorithms and machine learning techniques, researchers are now able to sift through the massive data sets collected by telescopes at unprecedented speeds. These technologies help scientists identify and classify celestial objects, uncovering patterns and anomalies that would have previously gone unnoticed. The insights gleaned from these analyses are essential for advancing our understanding of processes such as galaxy formation and the expansion of the cosmos. Beyond the realms of hard science, the humanities and social sciences also play a critical role in the broader landscape of cosmic research. They help us understand public perception and the philosophical questions that arise when we contemplate our place in the universe. For example, psychology and ethics contribute to more effective science communication, ensuring that researchers can engage the public in meaningful conversations about the implications of their discoveries. These interdisciplinary exchanges allow for a more nuanced understanding of the ethical considerations surrounding space exploration and the technologies that drive it, ensuring that progress is made in a responsible, inclusive way. Furthermore, collaborations extend into fields like chemistry and biology, particularly in the growing field of astrobiology. Here, the search for life beyond Earth blurs traditional scientific boundaries. By understanding the conditions that support life as we know it, scientists can explore exoplanets in the quest for extraterrestrial existence. This holistic, cross-disciplinary approach underscores the importance of synergy between diverse fields of study, showing that the most profound mysteries of the universe often require the combined insights of many different scientific inquiries. Equally important are educational and outreach programs, which serve as bridges between complex scientific concepts and the general public. These initiatives help transform abstract, technical ideas into accessible knowledge, fostering curiosity and engagement with the wonders of the cosmos. Educational outreach is not just about disseminating information, it's about inspiring the next generation of scientists, engineers, and explorers. Through hands-on activities, workshops, and interactive exhibits, young people are given the opportunity to experience the thrill of scientific discovery. This early exposure can ignite a lifelong passion for science, technology, engineering, and mathematics, STEM, shaping future careers and fueling innovations that may one day unlock new frontiers in space research. Outreach programs also play a crucial role in promoting inclusivity within the scientific community. By reaching out to underrepresented groups and communities, these initiatives strive to ensure that diverse voices contribute to the ongoing dialogue about space exploration. Public lectures, science fairs, and family-oriented events foster an environment where everyone, regardless of background or experience, can engage with the subject. This inclusivity enriches the field, bringing in fresh perspectives and ideas that drive innovation forward. Moreover, these programs help raise awareness about critical global challenges such as climate change and planetary protection. By illustrating the interconnectedness of space science with issues that affect life on Earth, they highlight the relevance of scientific research in addressing humanity's most pressing concerns. An informed public is more likely to support policies that ensure continued investment in space exploration, recognizing the long-term benefits that these endeavors bring to society. Public interest plays a vital role in shaping the direction of cosmic research. When people are captivated by topics like dark matter, black holes, or the origins of the universe, it can spark a collective enthusiasm that drives researchers to dig deeper into these fascinating mysteries. This public fascination often manifests in various forms, from school astronomy nights to community lectures, all of which fuel curiosity and encourage further exploration. The wonder of the public acts as a catalyst, pushing scientists to pursue new frontiers with greater vigor. Perhaps one of the most significant ways public interest influences space science is through funding. When scientific discoveries capture the public imagination, they often lead to increased financial support, both from governmental agencies and private organizations. For example, space missions and major discoveries often generate excitement, resulting in a surge of funding from agencies like NASA or the European Space Agency. This financial backing enables further advancements in technology and research, propelling space exploration to new heights. In conclusion, the pursuit of cosmic knowledge is not a solitary endeavor, but a complex, multifaceted journey that requires collaboration across scientific disciplines, effective public engagement, and robust funding mechanisms. As we continue to explore the universe, the interplay between theoretical models, observational data, and public interest will remain essential in guiding us toward new discoveries and expanding our understanding of the cosmos. Philanthropic contributions can play a pivotal role in accelerating research and exploration, especially in fields as dynamic and complex as space science. Wealthy individuals and organizations driven by a desire to advance our understanding of the cosmos often invest in projects that resonate not just with the scientific community, but with the public as well. These philanthropic efforts are crucial because they help bridge the gap between groundbreaking scientific inquiry and the resources needed to fuel such ambitious ventures. When individuals and institutions commit to supporting space research, they enable the development of cutting-edge technologies, such as powerful telescopes capable of exploring deeper into the universe than ever before. Public funding, bolstered by private investment, allows scientists to push the boundaries of what is possible in space exploration. As these technologies advance, they open new frontiers of discovery, providing us with tools that make the seemingly impossible achievable. For example, the development of telescopes that can capture faint light from distant stars and galaxies has revealed cosmic phenomena that were once hidden from our view. These instruments, equipped with advanced mirrors and detectors, enable us to see farther into space and farther back in time, shedding light on the mysteries of the universe. But it's not just about the technology. The collaboration between public and private sectors ensures that the public, too, is invested in these monumental discoveries. When the public perceives the value and potential of a scientific endeavor, it creates a ripple effect, inspiring greater support and engagement. This partnership between funding and curiosity fuels not just technological advancements, but a shared human endeavor to understand the universe. As we continue to uncover new cosmic mysteries, the intertwining of public interest and funding will remain essential. Through compelling storytelling and groundbreaking discoveries, scientists can continue to capture the public's imagination, ensuring that our journey to explore the universe is supported both financially and emotionally. This vital collaboration is integral to unraveling the deepest enigmas of the cosmos and expanding our knowledge of the universe in which we reside. With each new advancement, our ability to observe and comprehend the vastness of space is reshaped. In recent decades, advancements in telescopic technology have revolutionized our ability to peer into the universe. The development of larger and more sensitive instruments has allowed astronomers to see objects that were once invisible to the naked eye, objects that might hold the key to understanding the very fabric of the universe. The transition from optical telescopes, which rely on visible light, to a wider variety of instruments capable of detecting non-visible wavelengths has significantly broadened our observational capabilities. Radio telescopes, for instance, allow us to study celestial bodies that emit radio waves, such as distant pulsars and quasars. Meanwhile, infrared and ultraviolet telescopes open up new avenues for observing cooler objects or those obscured by interstellar dust. By using a multifaceted approach that includes different wavelengths of light, scientists can create a much more complete and nuanced picture of the universe, one that reveals phenomena that were previously hidden from our view. The launch of space-based telescopes, such as the Hubble Space Telescope, has further enhanced our ability to observe distant cosmic objects with greater clarity. Without the distortion caused by Earth's atmosphere, telescopes in space provide sharper, more detailed images, which have led to groundbreaking discoveries. Hubble's observations have been instrumental in advancing our understanding of dark matter, the expansion of the universe, and the formation of stars, among other critical areas. The recent launch of the James Webb Space Telescope promises to build on these achievements by offering unprecedented views of the early universe and the formation of galaxies, furthering our knowledge of cosmic evolution. These technological advances are not merely about capturing beautiful images. They represent a paradigm shift in how we comprehend the fundamental processes of the cosmos. As technology continues to evolve, we find ourselves on the cusp of discovering even greater mysteries. Telescopes capable of observing cosmic phenomena with extraordinary detail and clarity are just the beginning. Emerging technologies in fields like artificial intelligence, advanced propulsion, and material science are poised to transform the future of space exploration. Artificial intelligence, AI, has become an indispensable tool in modern space research. By analyzing vast datasets more efficiently than human researchers, AI algorithms can identify new celestial phenomena and patterns, enabling scientists to make faster and more accurate discoveries. This ability is especially important for studying exoplanets, planets located outside our solar system, which are often detected by measuring subtle changes in starlight. AI's ability to sift through enormous amounts of data and identify these faint signals has vastly improved our understanding of distant worlds. Meanwhile, advancements in reusable rocket technology are poised to revolutionize space travel. Private companies are investing heavily in systems that can launch and land multiple times, greatly reducing the cost and frequency of space missions. This breakthrough has the potential to make space exploration more accessible and flexible, allowing for more frequent missions and the possibility of conducting research and exploration in ways that were previously constrained by economic limitations. In addition to these innovations, advances in material science are contributing to the development of spacecraft that are not only more resilient, but also capable of withstanding the harsh conditions of deep space. Lightweight composites and heat-resistant materials are making it possible to design spacecraft that can survive extreme temperatures, high radiation levels, and intense pressure. These breakthroughs could pave the way for longer missions, allowing us to explore farther reaches of the solar system and beyond. Propulsion systems are also undergoing a transformation. Concepts like ion propulsion and nuclear thermal propulsion offer the potential for more efficient and faster space travel, allowing spacecraft to reach distant destinations in a fraction of the time required by conventional rocket engines. With these new propulsion technologies, the dream of sending human missions to Mars and beyond becomes increasingly feasible. As these technologies evolve, they will enable us to unlock new possibilities for exploration and discovery. One of the most profound challenges in modern cosmology is the study of dark matter, which accounts for most of the universe's mass, but remains invisible and undetectable by conventional means. For decades, scientists have struggled to understand this elusive substance. However, the rise of advanced computer simulations has provided a breakthrough. By simulating the behavior of dark matter alongside visible matter, researchers can now visualize how these unseen forces interact. These simulations allow scientists to model cosmic structures like galaxies and galaxy clusters, helping them understand how dark matter influences their formation and distribution. These detailed simulations have revealed some startling insights, such as the discovery of a vast cosmic web of dark matter that connects galaxies across the universe. This web-like structure, composed of dense nodes of galaxies linked by thin filaments of dark matter, outlines the large-scale architecture of the universe. These findings are not only fascinating, but also essential for refining our understanding of the cosmos. By predicting how these dark matter structures should appear in reality, astronomers can design observational strategies to test and refine these models. As technology advances and new discoveries unfold, the journey to understand the universe continues to accelerate. Each breakthrough, whether in telescopic technology, AI, propulsion systems, or material science, brings us closer to answering the age-old questions of our existence and the nature of the cosmos. With the support of both public and private investments, the mysteries of space are being unraveled at an unprecedented pace, opening new frontiers for scientific exploration and human understanding. The exponential growth of computational capabilities has not only transformed the way we observe and explore the universe, but also redefined the methodologies that govern astronomical research. The integration of sophisticated technologies into space exploration offers new avenues for understanding the cosmos, particularly through tools like space telescopes. These tools, such as the European Space Agency's Euclid mission, are instrumental in gathering invaluable data, particularly when it comes to enigmatic cosmic phenomena like dark matter. However, as these advancements unfold, the crucial role of computer simulations comes into play, providing a framework to interpret the complex data collected from these high-tech observational tools. By enabling scientists to simulate different theories of dark matter, computational models allow for more precise, nuanced understanding of this invisible substance that plays a key role in shaping the universe. The relationship between simulation and observation is a vital synergy that deepens our grasp of the forces that govern the cosmos. The evolution of artificial intelligence, AI, has further augmented this process, opening unprecedented doors in astronomical research. AI's role in analyzing vast quantities of astronomical data accelerates the pace of discovery, shedding light on mysteries that would otherwise remain hidden for decades. Yet the power of AI introduces its own set of ethical complexities. One of the most pressing concerns revolves around bias in AI algorithms. These systems are trained on massive data sets, and if those data sets contain biases, whether from incomplete information or skewed representation, the AI's conclusions could lead to inaccuracies, obscuring important findings, or misinterpreting data in a way that limits scientific progress. The consequence of such biases could be a failure to uncover celestial phenomena that are crucial to advancing our understanding of the universe. Moreover, as AI increasingly plays a role in unlocking the secrets of the cosmos, questions arise about authorship and accountability for the discoveries made by these systems. Should recognition go to the scientists who created and fine-tuned the AI? Or is it the AI itself that deserves credit? Or perhaps the institutions that funded the research should bear responsibility? As AI uncovers patterns and insights at a speed and depth that far exceeds human capabilities, establishing clear guidelines for attribution becomes essential for maintaining transparency and fostering trust within the scientific community. As with any powerful tool, the application of AI in astronomy also raises privacy concerns. The vast observational data collected from space probes, telescopes, and other technologies may unintentionally reveal sensitive information about both celestial objects and Earth's environment. Such data, often gathered from a variety of sources, could hold unintended privacy risks, necessitating stringent measures for responsible data handling. Ensuring that data is used ethically and with proper safeguards is paramount in maintaining scientific integrity and public confidence. Furthermore, there are significant risks related to the dual-use nature of AI technology. Initially developed for peaceful scientific purposes, these advancements could be misappropriated for surveillance or military uses. The potential for AI to be weaponized or used in ways that could compromise global security calls for urgent discussions on ethical regulations and responsible use. It is essential for scientists and engineers to engage with these ethical dilemmas as we push further into uncharted territory in space exploration. Space probes remain some of the most critical instruments in our quest to explore regions far beyond our solar system. These meticulously designed machines travel vast distances to gather data that cannot be captured by telescopes or other remote observational methods. One of the most remarkable examples is the Voyager spacecraft, which has traveled far past the outer planets of our solar system and into the far reaches of interstellar space. Voyager's mission has provided us with invaluable insights into cosmic rays, magnetic fields, and the conditions of the interstellar medium, offering a rare glimpse into the frontier where our solar system meets the greater universe. Other space missions, such as the New Horizons probe, continue to shed light on our solar system's distant corners. By studying objects in the Kuiper Belt, like Pluto and its moons, these missions reveal ancient records of the solar system's formation and evolution. These icy bodies serve as time capsules, preserving a wealth of information about the early days of our cosmic neighborhood. Understanding these distant objects is key to piecing together the broader story of planetary formation and the potential for life beyond Earth. As technology advances, the capabilities of space probes also continue to improve. Missions like the Parker Solar Probe are pushing the limits of our knowledge, studying the sun's outer atmosphere to uncover new information about solar winds and space weather. The data collected will deepen our understanding of how our sun influences the entire heliosphere, the vast bubble of solar wind that envelops our solar system. This, in turn, will provide insight into how interstellar space interacts with the solar system. These space probes do more than satiate our curiosity. They shape our understanding of the universe's origins, evolution, and ultimate fate. Each new discovery adds a piece to the cosmic puzzle, igniting an enduring passion for exploration that spans generations. As we continue to make groundbreaking advances, these robotic pioneers offer critical data that shapes not only our scientific knowledge, but also our collective imagination. The role of satellites in modern astronomical research has become increasingly crucial, allowing scientists to observe and analyze cosmic phenomena in ways that were once thought impossible. Equipped with cutting-edge sensors, these advanced instruments gather a wide range of data, from detecting various wavelengths of light, such as ultraviolet or infrared, to studying the characteristics of distant stars and galaxies. Such technologies provide a clearer picture of the universe, revealing phenomena that would otherwise remain invisible to human eyes. They also serve a dual purpose by monitoring Earth's own environment, allowing researchers to draw connections between cosmic events and their potential impacts on life on Earth, whether through climate change or asteroid collisions. Satellites, through high-resolution imaging, have also contributed to remarkable discoveries, such as the identification of exoplanets. By capturing detailed images and analyzing surface features of planets and moons within our solar system, these instruments provide valuable data on geological structures and signs of past or present life. This information not only deepens our scientific understanding, but also captures the public's imagination, fueling interest in space exploration. Looking ahead, the next generation of satellites promises even more sophisticated sensors, including artificial intelligence systems capable of analyzing data in real time. These advancements will empower scientists to respond swiftly to cosmic events, further refining our understanding of the universe. With each new discovery, the boundaries of space exploration expand, reshaping our view of the cosmos and our place within it. In parallel with these advancements, big data is revolutionizing modern astrophysics. The ability to process and analyze enormous datasets has allowed scientists to study celestial phenomena on an unprecedented scale. The combination of powerful computing systems and advanced data collection tools, such as telescopes and satellites, enables astronomers to gather massive amounts of information about stars, galaxies, and other cosmic events. These massive datasets, often containing details from millions of celestial objects, allow researchers to build an ever more comprehensive picture of the universe. Projects like the Large Synoptic Survey Telescope are prime examples of how big data is changing the landscape of astronomy. Designed to capture a significant portion of the night sky, this telescope will generate petabytes of data, presenting both a challenge and an opportunity for scientists. The sheer volume of data collected will require sophisticated machine learning algorithms to process and analyze, enabling astronomers to detect patterns, classify objects, and even identify new celestial bodies at an unprecedented rate. As these datasets grow, they provide an increasingly nuanced view of the universe, enhancing our understanding of its formation, evolution, and structure. In sum, the future of space exploration is shaped by the convergence of computational power, advanced sensors, and artificial intelligence. As these technologies continue to evolve, they promise to unlock even more profound mysteries of the cosmos, transforming our understanding of the universe and our place within it. Big data is fundamentally transforming the landscape of scientific research, creating unprecedented opportunities for global collaboration. Researchers and scientists from different corners of the world now have the ability to access and analyze the same datasets in real time, enabling a more interconnected approach to solving complex scientific problems. This digital sharing of knowledge has paved the way for groundbreaking joint research projects and a host of shared discoveries. The Event Horizon Telescope, which captured the first ever image of a black hole, serves as a powerful example of how pooling expertise and data from across the globe can lead to monumental findings. This international cooperation accelerates our understanding of astrophysical phenomena, pushing the boundaries of what we thought we knew about the cosmos. Moreover, big data is enhancing simulations and refining theoretical models in astrophysics. Researchers now have access to real observational data, which allows them to fine-tune their simulations and improve predictions about cosmic events. Theories regarding some of the universe's most mysterious phenomena, such as gravity, dark matter, and dark energy, are being constantly updated and enhanced through the integration of observational insights. This synergy between real-world data and theoretical modeling helps bridge the gap between the raw observations of the universe and the fundamental principles of physics that govern it. Ultimately, this dynamic interplay is leading to a more comprehensive understanding of the cosmos and humanity's place within it. Public engagement with science is also undergoing a profound transformation, thanks to mobile applications and digital platforms. These tools are not just enhancing scientific literacy, they are revolutionizing the way people interact with space. With the tap of a button, users have access to an ever-growing wealth of information, from the latest discoveries to in-depth educational resources. Whether tracking celestial events, exploring distant galaxies, or learning about the core principles of astrophysics, these platforms allow individuals to engage with the wonders of the universe at their own pace. This accessibility fosters curiosity and makes complex scientific concepts much more approachable. Many of these applications are designed with interactive features that encourage users to participate in hands-on learning. Augmented reality tools, for instance, allow users to visualize constellations, planets, and other celestial objects right from their own backyards. This personal connection with the universe creates a sense of awe and wonder, which deepens users' understanding of the material. In addition, gamification elements in some apps motivate users to engage further by completing quizzes or challenges, turning learning into an enjoyable and rewarding experience. These interactive features transform the way we explore space, making the subject matter more tangible and engaging. Furthermore, social media platforms and online forums have become essential in amplifying scientific literacy efforts. These digital spaces foster communities where enthusiasts, from novices to experts, can engage in open discussions, share ideas, and exchange insights. By connecting people from diverse backgrounds, these platforms allow for the cross-pollination of ideas and perspectives, enriching our understanding of space and making complex topics more relatable. In this collaborative environment, individuals can support each other's learning journeys, creating a community of like-minded explorers united by their curiosity about the universe. The growing partnerships between educational institutions and tech companies are also playing a pivotal role in transforming STEM education. Many of these initiatives are designed with an emphasis on inclusivity, ensuring that cutting-edge educational resources are available to a wide audience. By leveraging technology, these projects not only inspire the next generation of scientists and engineers, but also create a more informed and engaged public. With greater access to scientific knowledge and tools, individuals can become active participants in the ongoing dialogue about space, rather than merely passive consumers of information. Modern communication technologies are also playing a crucial role in facilitating international collaboration in space research. High-speed internet, satellites, and advanced video conferencing tools have made it easier than ever for scientists from around the world to connect in real time. This global connectivity allows research teams to tackle the complex challenges of space exploration together, regardless of geographic location. Cloud computing, in particular, has emerged as a game-changing tool. By utilizing shared online platforms, researchers can store and access vast amounts of data without being constrained by physical location. Whether working in a lab in Japan or conducting field research in Brazil, scientists can collaborate effortlessly, accelerating the pace of innovation and improving the quality of research outcomes. The seamless exchange of ideas has also been enhanced by digital communication tools such as instant messaging and social media. These platforms allow researchers to quickly share updates, ask questions, and solicit feedback from colleagues across the globe. This rapid flow of information stimulates new ideas and encourages a culture of shared learning, which is crucial when addressing the multifaceted problems of space science. Additionally, international conferences and virtual symposiums have become more inclusive, thanks to advances in communication technology. Scientists can now present their research and engage in meaningful discussions without the need for extensive travel, further democratizing the exchange of scientific knowledge. The ongoing expansion of space exploration is also acting as a catalyst for technological innovation in fields that extend far beyond astrophysics. The challenges faced by scientists and engineers as they explore the cosmos often lead to breakthroughs that have a profound impact on life here on Earth. For example, the demand for more efficient energy systems in spacecraft has spurred advancements in solar panel technology, which in turn makes solar energy more viable for use in homes and businesses. Space missions also drive significant progress in materials science. The extreme conditions in space, such as intense radiation and extreme temperatures, require the development of materials that can withstand these harsh environments. The innovations that arise from this research are finding applications in a range of industries, from construction to healthcare. Some of the materials developed for space missions, like heat-resistant insulation, have been adapted for use in fire-resistant clothing and improved building insulation. This creates a direct link between space exploration and consumer technology, underscoring the broader impact of space research on everyday life. In summary, big data and modern technologies are not just transforming the way we conduct space research, but are also democratizing science, fostering collaboration across borders, and enriching the lives of everyday people. Through these advances, the boundaries of knowledge are constantly expanding, and humanity is taking ever bolder steps toward understanding the vast, mysterious universe in which we live. As these efforts continue to evolve, they promise to accelerate both our scientific discoveries and our ability to apply those discoveries in ways that improve life on Earth. The development of robotic systems for planetary exploration has sparked a cascade of technological innovations that extend far beyond the confines of space. As humanity ventures into the unknown reaches of our solar system, these advancements have catalyzed breakthroughs in automation and artificial intelligence. These technologies are not limited to space exploration, but are now shaping industries ranging from healthcare to manufacturing. For example, Robotic surgery has dramatically benefited from the precision required in space robotics. The fine-tuned algorithms and mechanisms designed for navigating distant terrains have translated into safer, more effective surgical procedures, enhancing patient outcomes worldwide. In the realm of autonomous vehicles, the technologies that drive planetary rovers have been instrumental in refining mapping systems and navigation algorithms. These developments, originally conceived for space exploration, are now revolutionizing how we think about and interact with vehicles on Earth, making them smarter, safer, and more efficient. Thus, the boundaries of space exploration not only expand our knowledge of the universe, but also push the envelope on technological frontiers that touch every aspect of life on Earth. The ripple effect of space exploration extends even further, touching the vast world of communications. Maintaining contact with spacecraft exploring distant planets has led to significant advancements in satellite technology. These improvements, initially designed to ensure stable communication with far-off space missions, have directly benefited global communications infrastructure. This includes enhancing internet connectivity, expanding mobile networks, and offering more reliable communication systems to millions of people worldwide. Innovations that were once considered exclusive to space missions are now part of our everyday lives, demonstrating how deeply interconnected space exploration is with global technological progress. As humanity continues to push beyond the boundaries of our planet, the technologies emerging from these efforts will undoubtedly continue to shape industries in ways we cannot yet fully predict. These innovations promise to not only enhance life on Earth, but also bring about unexpected improvements in areas ranging from transportation to energy efficiency, all stemming from our quest to explore the cosmos. Yet, as we venture farther into space, the discovery of extraterrestrial intelligence looms as one of the most profound possibilities of all. Such a discovery would shake the foundations of our understanding of the universe and humanity's place within it. For millennia, we have pondered the question of whether we are truly alone in the cosmos. Finding intelligent life beyond Earth would not only confirm that life can take many forms, but would also prompt a deep rethinking of our role in the grand scheme of existence. This revelation could encourage a reevaluation of the processes of evolution, offering new insights into how life might emerge and thrive under vastly different conditions. If we were to encounter an extraterrestrial civilization, the knowledge shared by these beings could open new avenues for understanding the origins of life and the conditions necessary for it to flourish. Their experiences and technologies might offer answers to long-standing questions about the universe's formation, shedding light on the myriad pathways that evolution can take. In this way, discovery of extraterrestrial intelligence could illuminate not only the origins of life beyond Earth, but also deepen our understanding of biology, evolutionary theory, and the potential for life elsewhere. The implications of such a discovery would not be limited to the scientific realm. The existence of intelligent extraterrestrial life would spark profound philosophical and sociological debates. It would challenge our worldview, compelling us to reconsider beliefs about religion, morality, and our place in the cosmos. The knowledge that we are not the pinnacle of intelligent life might foster a new sense of humility, creating a deeper connection between humanity and the universe. This realization could reshape the way we view ourselves, encouraging us to see our species as part of a broader, interconnected cosmic narrative. At the same time, the potential for communication, or the lack thereof, with extraterrestrial civilizations would raise significant ethical questions. How should we treat other intelligent life forms, especially if they are vastly different from ourselves? What responsibilities do we have as we engage with these beings, whether through peaceful cooperation or conflict? These questions would challenge us to rethink our strategies for diplomacy, both on Earth and, potentially, beyond. If we are to engage with other civilizations, we will need to approach them with a deep sense of respect and understanding, perhaps shifting our perspective on interstellar relations and our capacity for coexistence. This entire scenario underscores the vastness of the unknown. As humanity stands on the brink of potentially discovering extraterrestrial intelligence, the implications of such a finding would reverberate through every corner of human thought. Researchers are already exploring the mysteries of the universe, and future discoveries could dramatically reshape our understanding of fundamental phenomena like gravity. Anomalies in gravitational behavior, such as those observed in dark matter and dark energy, challenge our current models of physics, suggesting that the universe operates under principles we have yet to fully comprehend. The development of advanced observational technologies, including gravitational wave detectors and next-generation telescopes, may soon provide new insights into these cosmic anomalies. These breakthroughs could unveil unexpected gravitational behaviors associated with massive cosmic events like black hole mergers or neutron star collisions. As scientists collect more data, they may refine existing gravitational models or propose entirely new theories to account for these phenomena. These findings could lead to a deeper understanding of space-time itself, potentially revealing new dimensions or variations in the fundamental forces that govern the cosmos. Moreover, exploring exotic states of matter in extreme environments, such as within neutron stars or during the early universe, could unlock entirely new realms of discovery. Understanding how gravity interacts with these intense conditions could lead to the revelation of new forces or modify our existing theories of gravity. As we explore the universe's most extreme environments, we may uncover a deeper, more unified understanding of gravity, potentially linking it with quantum mechanics in ways we cannot yet predict. These discoveries will not only illuminate the gravitational anomalies we observe, but will also provide new insights into the broader structure of the universe. By embracing the mysteries posed by these phenomena, we are likely to refine our cosmological models and perhaps uncover the very nature of gravity itself. One of the most profound enigmas in modern cosmology remains dark matter, which, though invisible to our eyes, makes its presence known through its gravitational effects on visible matter. While scientists have yet to observe dark matter directly, they infer its existence from the way it influences the movement of galaxies and clusters of galaxies. Various theories have been proposed to explain dark matter's elusive nature. One such theory posits that dark matter is composed of weakly interacting massive particles, or WIMPs. These particles, which interact only through gravity and the weak nuclear force, are predicted to be heavy, making them extraordinarily difficult to detect. Despite numerous experiments designed to detect these particles, they have yet to be observed directly, sparking ongoing debates about their existence. Another intriguing theory suggests that cosmic strings, one-dimensional defects that may have formed in the early universe, could be responsible for the gravitational effects attributed to dark matter. These strings, if they exist, could warp space-time around them in ways that mimic the gravitational influence of dark matter. If cosmic strings are real, they could significantly influence the dynamics of galaxies and galaxy clusters, albeit in ways that differ from the traditional models of dark matter. As researchers continue to explore these ideas, the search for dark matter and the study of cosmic strings will remain at the forefront of cosmological inquiry, holding the potential for groundbreaking discoveries that could revolutionize our understanding of the universe's fundamental forces. Some researchers are now exploring groundbreaking modifications to our understanding of gravity itself. Theories like modified Newtonian dynamics suggest that gravity behaves differently on large cosmic scales compared to the traditional understanding presented by Newtonian and Einsteinian physics. According to these alternative theories, the effects we attribute to dark matter might be explained by altering the laws of gravity, rendering the need for dark matter obsolete. Instead of assuming the existence of invisible, undetectable particles that exert gravitational effects, these theories propose that gravity's influence could simply be more complex than we've previously realized. As our observational tools improve and more data becomes available, the scientific community is vigorously testing these hypotheses. The search for clues continues, with the ultimate goal of unraveling the true nature of dark matter, an elusive substance believed to make up a significant portion of the universe. In this ever-evolving quest, new advancements in quantum mechanics hold the potential to profoundly alter how we explore the very fabric of the cosmos. At the heart of this revolution lies the principle of superposition in quantum mechanics. This fascinating concept suggests that particles can exist in multiple states simultaneously, only choosing a definite state once they are observed or measured. This idea could pave the way for the development of revolutionary quantum technologies, including highly sensitive quantum sensors. Such devices could allow us to detect gravitational waves or subtle fluctuations in cosmic background radiation with unprecedented precision. The ability to measure these phenomena with such clarity would deepen our understanding of the universe, providing us with insights into the most intricate workings of the cosmos. Furthermore, quantum entanglement, an enigmatic phenomenon where the state of one particle is instantaneously correlated with another, could have profound implications for how we communicate and observe space. Picture a network of quantum entangled particles distributed across vast distances of space, enabling the instantaneous sharing of data regardless of the space between them. This could transform our ability to monitor distant celestial events, from the explosive power of supernovae to the delicate dance of galaxies. Real-time insights into these events, which were once the realm of science fiction, could soon become a reality. Quantum mechanics may also enhance our theoretical understanding of the universe. By applying the principles of quantum field theory to cosmology, we could gain a better understanding of the mysterious forces driving the expansion of the universe, such as dark energy. The concept of quantum fluctuations present in the early universe might help scientists piece together how the cosmos evolved from a singularity into the vast, complex structure we observe today. As we continue to explore these quantum frontiers, the very foundations of our understanding of cosmic phenomena are poised for transformation. The intersection of quantum mechanics and cosmology could inspire a shift in how we perceive our place in the universe, challenging long-held assumptions and inviting a fresh perspective on both the microscopic and macroscopic realms of existence. The universe is vast and largely unexplored, offering a thrilling frontier for the discovery of entirely new cosmic objects. With the advancement of technology and observational techniques, we are now able to probe deeper into the cosmos than ever before. The launch of powerful telescopes, both space-based and ground-based, allows us to push the boundaries of what we can observe, opening the door to encounters with phenomena that were once unimaginable. Some of the most intriguing regions of space, the depths of intergalactic space or the far reaches of distant galaxies, may contain unique objects shaped by conditions we have yet to fully comprehend. Scientists speculate that we may discover entirely new types of stars, exotic remnants from the early universe, or even strange forms of dark matter. These new discoveries could challenge the very foundations of astrophysical theories and expand our understanding of cosmic evolution. There is also a growing interest in what lies beneath the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates the entire universe. This radiation has long been a critical tool in understanding the early universe, but beneath its glow, there may be hidden structures or phenomena that could completely redefine our understanding of cosmic history. Perhaps we will uncover stars that behave in radically different ways than the ones we know, or new classes of planets orbiting distant stars under conditions we have never before observed. As our search continues, the development of novel technologies is allowing astronomers to refine their quest for these elusive objects. Next-generation observatories, capable of scanning the universe in unprecedented detail, place us on the cusp of potentially revolutionary discoveries. Each scan offers the promise of uncovering mysteries that have long eluded our grasp. These discoveries could reshape centuries of cosmic inquiry, reminding us that beyond the horizon of our current knowledge lies a universe still full of secrets waiting to be revealed. Among the most fascinating phenomena in the universe are quasars, highly luminous, energetic objects formed during the early stages of the universe's evolution. These objects, powered by supermassive black holes at the centers of distant galaxies, can emit enough energy to outshine entire galaxies. Quasars are invaluable tools for understanding the history of the cosmos, yet they hold even more mysteries waiting to be uncovered. One intriguing aspect of quasars is their rapid variability in brightness. Some quasars can change their luminosity over a matter of days or even hours, raising important questions about the complex dynamics at play within the accretion disks surrounding their black holes. This variability could offer new insights into the behavior of matter under extreme conditions, potentially leading to revised theories about how black holes function and how galaxies evolve. Additionally, many quasars emit powerful jets of material that can stretch across vast distances in space. These jets have been linked to phenomena such as gamma-ray bursts and cosmic ray production. Investigating the composition, speed, and behavior of these jets could reveal important clues about how quasars impact their host galaxies and the surrounding intergalactic medium. As observational technology continues to advance, we may discover that these jets play a far more significant role in the formation and evolution of galaxies than we currently understand. In summary, the universe remains an incredibly dynamic and mysterious place, with each new discovery potentially rewriting our understanding of cosmic forces and phenomena. As technology advances, scientists are poised to peel back the layers of the cosmos, uncovering new objects, forces, and behaviors that will push the boundaries of knowledge even further. The journey to understand the universe is far from complete, and the future holds an exciting array of revelations yet to be discovered. Quasars, some of the most captivating objects in the universe, offer an extraordinary opportunity for scientists to explore the distant past of our cosmos. These luminous beacons, located millions or even billions of light years away, serve as cosmic time machines, shedding light on the early stages of the universe. As light from a quasar travels across the vast expanse of space, it carries with it a redshift, a shift in wavelength that provides valuable clues about the conditions of the universe at the time the light was emitted. The further away a quasar is, the older the light, allowing researchers to peer into different epochs, observing the universe as it appeared at various points in history. As modern observational techniques continue to evolve and more powerful telescopes are launched into space, scientists are uncovering deeper connections between quasars and the formation of the first galaxies and stars. The relationship between these enigmatic objects and the earliest structures of the cosmos is still largely speculative, but every new discovery brings us closer to understanding the profound processes that shape the universe. These links could transform our perception of cosmic history, possibly offering insight into the very origins of matter, light, and space itself. Beyond their role as historical witnesses, quasars also present opportunities for future research into the still unknown properties of the universe. Their extreme environments, vast energy outputs, powerful jets of particles, and intense gravitational fields challenge our understanding of physics and offer a window into realms we have yet to explore. As scientists continue to study quasars, new and unexpected phenomena will likely emerge, expanding our knowledge of the universe and potentially revising existing theories about its formation, structure, and evolution. At the same time, another fundamental force in our exploration of the cosmos is consciousness. A phenomenon we often take for granted, consciousness plays an integral role in our understanding of the universe. As humans, our curiosity about the cosmos is shaped not only by our observations of stars, galaxies, and distant nebulae, but also by our very ability to perceive and interpret these wonders. The act of observing is not as passive as it might seem. Consciousness itself seems to influence the way we interact with reality. Some theorists even suggest that consciousness is not merely a byproduct of brain activity, but may be a fundamental aspect of the universe itself, potentially embedded in the very fabric of reality. Emerging theories in quantum mechanics propose that the very act of observation can alter the behavior of particles, implying a deep connection between the observer and the observed. This suggests that our conscious awareness might affect the universe at its most fundamental level, creating a bridge between subjective experience and objective reality. This interplay between consciousness and the cosmos opens up profound questions about the nature of existence, purpose, and the role of human awareness in shaping the universe around us. As we delve deeper into the mysteries of consciousness, we find that it is not just a scientific curiosity, but a cornerstone of our philosophical inquiry into the meaning of life and the nature of reality. Our capacity for thought, Awareness and reflection has led us to construct narratives, symbols, and theories that help us make sense of the vast, unknown universe. By exploring how consciousness interacts with the cosmos, we gain not only scientific knowledge, but also a deeper understanding of what it means to exist in this vast, interconnected reality. This exploration brings us to the future of the universe itself, where various theories seek to predict the ultimate fate of everything we know. One of the most widely discussed hypotheses is the Big Freeze, a scenario in which the universe's expansion continues indefinitely. Over time, this expansion would cause the universe to cool, eventually reaching temperatures close to absolute zero. In this frozen state, stars would burn out, galaxies would drift apart, and dark energy would dominate the universe, leaving vast, empty spaces in its wake. The universe would become an inhospitable, cold void, devoid of life as we know it. On the other hand, there's the possibility of the Big Crunch, in which the expansion of the universe halts and reverses itself. Gravitational forces could pull matter back toward a single point, leading to a dramatic contraction of the universe. This contraction could culminate in a cosmic collapse, potentially triggering a new Big Bang and ushering in a new cycle of cosmic expansion. This cyclical model of the universe suggests a never-ending series of births and deaths of cosmic structures, a concept that has intrigued theoretical physicists for decades. An even more dramatic fate for the universe is the Big Rip, a theory that hinges on the continued acceleration of the universe's expansion due to dark energy. If dark energy grows stronger over time, it could tear apart galaxies, stars, and even the very fabric of space-time itself. This scenario envisions a universe gradually disintegrating into nothingness, raising unsettling questions about the ultimate destiny of all matter and energy. Each of these possibilities, though speculative, encourages us to reflect on the future of our universe. As our observational methods improve, we may gather evidence that will either support one of these theories or reveal new possibilities altogether. The future of the universe is one of the greatest and most awe-inspiring puzzles of modern science, one that calls for both imagination and rigorous inquiry. In the ongoing dance between chaos and order, the universe reveals its most complex and fascinating features. Galaxies, for example, embody this dynamic interplay. On the surface, the graceful, swirling arms of galaxies seem to represent a picture of perfect order. However, beneath this apparent tranquility lies a tumultuous environment marked by intense gravitational turbulence, star-forming regions, and occasional violent bursts of activity. This balance between order and chaos is not just an abstract concept. It is the driving force behind the continual creation and destruction that shapes the cosmos. One of the most perplexing aspects of this cosmic chaos is the role of dark matter. While scientists are still uncertain about its true nature, dark matter is thought to be a crucial component in holding galaxies together. Its invisible influence helps explain the unusual rotation patterns of galaxies and their interactions within clusters. However, the specifics of how dark matter interacts with visible matter remain a mystery, and its elusive behavior continues to challenge physicists. Another fascinating phenomenon arising from this cosmic chaos is gravitational lensing. This occurs when the light from a distant object, such as a galaxy or a quasar, is bent by the intense gravitational pull of a massive object, like another galaxy or a black hole. This bending of light acts as a cosmic magnifying glass, allowing scientists to study distant objects that would otherwise be too far away or faint to observe. Gravitational lensing provides one of the most direct ways to detect the presence of dark matter, revealing its influence on the visible universe and offering a tantalizing glimpse into the nature of this mysterious substance. The universe, with all its beauty and complexity, remains an open book, waiting for humanity to decode its many secrets. Each discovery, whether it concerns the distant past, the present state of the cosmos, or the future that lies ahead, offers us a deeper understanding of the forces and phenomena that shape our reality. The study of quasars, dark matter, consciousness, and the fate of the universe itself is far from complete. And as new technologies emerge and our theories evolve, the mysteries of the cosmos will continue to unfold, challenging us to expand our horizons and rethink everything we know about the universe and our place within it. The delicate and complex relationship between chaos and order offers a profound lens through which to view the universe. It is an eternal dance, constantly unfolding in processes both grand and minute, and can be seen in the most unexpected places, such as the birth of stars. When we look into star formation regions, we might perceive a uniform spread of gas and dust. However, this uniformity is an illusion, for the underlying reality is far more intricate. Tiny fluctuations, barely detectable in the chaotic sea of particles, can initiate significant events. These subtle variances in density trigger gravitational collapses, giving birth to new stars. And yet this birth is not a calm one. The surrounding conditions remain in a state of turmoil, where chaos reigns. Supernova explosions rip through space, releasing enormous amounts of energy and matter into the cosmos. The after effects of these stellar deaths are equally dramatic, sometimes resulting in the formation of neutron stars or black holes, objects of extreme density and gravitational pull. Each event reshapes the cosmic landscape, continuing a perpetual cycle of creation and destruction. Every twist and turn in this cycle raises profound questions about the very nature of existence, the life cycles of stars, the formation of planets, and ultimately, the possibility of life itself. As we venture deeper into the mysteries of the universe, the interplay between chaos and order demands our attention. This relationship invites astronomers and physicists alike to refine their models and ask questions that probe both the vast and the minuscule dimensions of the universe. How do these forces, chaotic and orderly, work together to shape galaxies, stars, and planetary systems? Each discovery we make brings us a step closer to unveiling the intricate structure of the cosmos. What seems to be random or chaotic might follow a deeply embedded order, one that we are only beginning to perceive. One of the most tantalizing frontiers in this quest to understand the cosmos lies in the mysterious phenomena of dark matter and dark energy. These invisible forces, which make up nearly 95% of the universe, remain largely unknown. Though we can infer their existence through their gravitational effects on visible matter, their true nature continues to elude us. Could future advancements in technology enable us to directly detect dark matter particles? Could new methods of observing the expansion of the universe reveal the hidden influence of dark energy? These questions propel much of modern astrophysical research. As we edge closer to answers, we may uncover the fundamental forces that drive the evolution of the universe, forces that govern everything from the smallest particles to the vast galaxies. Equally captivating is the search for exoplanets, particularly those within the habitable zones of their stars, regions where conditions might be right for life to arise. With the development of next-generation telescopes and more sophisticated imaging techniques, scientists are now able to explore the atmospheres of these distant worlds. By analyzing the chemical makeup of exoplanet atmospheres, we could detect molecules such as oxygen or methane, key indicators that life, as we know it, might exist elsewhere. This could not only transform our understanding of life, but revolutionize our concept of what constitutes a habitable environment in the cosmos. The discovery of such life would expand the very definition of life itself, suggesting that life could emerge in ways we never previously imagined. Another thrilling frontier in modern astrophysics is the study of gravitational waves. Since the first detection of these waves in 2015, we have gained a new way to observe cosmic phenomena that was once beyond our reach. Gravitational waves are ripples in spacetime caused by massive objects, like black holes or neutron stars, interacting with one another. As detectors improve, we will be able to observe more subtle and distant cosmic events, such as the collision of black holes or the merger of neutron stars. These observations could offer unprecedented insights into the fundamental forces of nature and the evolution of the universe, giving us a deeper understanding of the very fabric of spacetime. Equally transformative is the pursuit of understanding quantum gravity, a field that aims to reconcile two of the most powerful theories in physics, general relativity and quantum mechanics. These theories describe the universe at vastly different scales. General relativity governing the behavior of large cosmic structures like galaxies, and quantum mechanics describing the behavior of subatomic particles. The challenge lies in integrating these two frameworks into a single theory that works at all scales. New theories of quantum gravity could reshape our understanding of space-time, time itself, and the universe's structure at its most fundamental level. In doing so, they may challenge concepts that have held sway for centuries, fundamentally altering our perception of reality. Each of these frontiers, from dark matter to quantum gravity, pushes the boundaries of human knowledge. They not only expand our scientific horizons, but fuel our innate curiosity, the desire to explore the unknown. This curiosity has driven humanity from the dawn of civilization, when our ancestors gazed up at the stars in wonder, to the present day, where we deploy advanced space telescopes and launch exploratory missions into the far reaches of the solar system. Our thirst for understanding is not just intellectual, it is deeply personal, rooted in the profound questions that have always haunted us. Why are we here? How did everything begin? What lies beyond the visible sky? Yet as we gain answers, we find ourselves confronted by new questions. Our understanding of the fundamental forces governing the universe has advanced significantly, yet we remain in the dark about the nature of dark matter and dark energy, two forces that together make up nearly 95% of the universe's energy content. Their mystery is not a deterrent, however. Instead, it drives us forward, fueling the quest for knowledge that defines humanity's exploration of the cosmos. Each discovery, no matter how small, only opens up more avenues for inquiry. Our curiosity is boundless, and as we continue to peer deeper into the universe, we find that the more we know, the more there is to discover. The mystery of the universe, with its infinite expanse and unfathomable depths, continues to captivate the human soul. It stirs a profound sense of awe, invoking emotions that resonate deeply within our psyche. This fascination is not limited to scientists alone. It reaches across cultures, inspiring individuals from all walks of life, artists, writers, philosophers, and dreamers alike. There is a universal human experience tied to gazing at the night sky, a shared wonderment that transcends time, place, and background. The heavens beckon us, urging us to reflect on our existence within the vast cosmos. In the modern era, technological and scientific advancements only deepen this sense of curiosity. Each new leap in our observational abilities, whether through telescopes that peer deeper into space or satellites that map distant galaxies, unveils extraordinary phenomena. From the discovery of exoplanets in distant star systems to the enigmatic behavior of black holes and neutron stars, our understanding expands in ways previously unimaginable. And with the ever-growing likelihood of extraterrestrial life, the quest to decode the secrets of the universe remains as compelling as ever. As we push the boundaries of what we know, we remain ever conscious of how much remains unexplored, keeping the flame of curiosity alight throughout history. Thousands of years ago, long before the age of telescopes and satellites, ancient civilizations looked to the heavens with a similar sense of awe and purpose. The Babylonians, the Mayans, the Egyptians, each of these cultures studied the night sky with incredible precision. They didn't merely observe celestial bodies, they sought to understand their movements and the deeper meanings behind them. They created elaborate calendars, tracked the cycles of the moon and planets, and integrated this knowledge into their daily lives. For the Babylonians, these observations weren't just about science. They were bound to religious practices and agricultural rhythms, linking the divine to the physical world. The Greeks, a few centuries later, expanded upon this knowledge, adding layers of intellectual rigor and philosophical inquiry. Thinkers like Ptolemy and Aristarchus proposed groundbreaking ideas such as the geocentric model of the universe, which posited that the Earth was the center of all things. While this model was ultimately overturned, it provided the necessary framework for future astronomers and philosophers to ask bigger questions. The philosophical discussions about the cosmos during this era laid the groundwork for the scientific revolutions that would follow. This intellectual tradition sparked an enduring thirst for knowledge that spanned centuries, influencing scientists, mathematicians, and thinkers throughout the ages. Meanwhile, the Mayans exhibited a remarkable level of sophistication in their understanding of astronomy. Through painstakingly carved stone tablets and the development of their famous calendar system, they mapped the cycles of the moon, Venus, and other celestial bodies with an accuracy that still impresses modern astronomers today. Their deep understanding of the cosmos was intertwined with both their religious ceremonies and their agricultural practices, with celestial phenomena often serving as divine omens for the seasons ahead. These ancient interpretations of the heavens continue to provide invaluable insights into the historical movement of celestial bodies, further bridging the gap between ancient cultures and the modern scientific world. In many ways, the efforts of these ancient civilizations form the foundation of modern astronomy. Their methods of observation, documentation, and interpretation laid the groundwork upon which today's technological innovations and space explorations are built. As we continue to send probes to distant planets and observe galaxies billions of light years away, we stand on the shoulders of these early stargazers, reminded that the quest to understand the universe is as ancient as humanity itself. The relationship between science and art has long been intertwined, particularly when it comes to interpreting and understanding the cosmos. Throughout history, art and literature have served as mirrors reflecting humanity's deepest fears, hopes, and curiosities about the universe. Through the lens of fiction, poets, novelists, and artists have explored ideas about space, time, and existence, often pushing the boundaries of what was scientifically conceivable at the time. Works like those of Arthur C. Clarke and Isaac Asimov did not merely entertain readers. They inspired entire generations of scientists to consider the possibilities of space exploration and artificial intelligence. These visionary authors helped shape the discourse surrounding space, blending imagination with scientific inquiry to open new avenues of exploration. The connection between fiction and scientific discovery is not one-sided. In fact, literary and artistic interpretations often provide new perspectives that challenge scientists to think differently. What may seem like a fantastical concept in a novel might spark a new hypothesis or even a groundbreaking experiment. The famous warp drive from Star Trek, once considered pure science fiction, has since inspired real-world research into faster-than-light travel. Similarly, artists play a crucial role in transforming complex scientific ideas, such as quantum mechanics or the curvature of space, into visual representations that are accessible to the public. Through vivid illustrations, sculptures, or installations, these artists bridge the gap between highly technical concepts and everyday understanding. Their works invite both the scientific community and the general public to engage with abstract ideas in tangible, emotional ways. The integration of art and science is not merely a matter of aesthetics. It serves an educational purpose as well. In classrooms around the world, art and storytelling are used as tools to explain the complexities of the universe. By appealing to our imagination and emotional faculties, these creative expressions make difficult scientific concepts more approachable. They engage students not just intellectually, but emotionally, fueling their curiosity and passion for scientific discovery. This intersection of creativity and inquiry is what drives progress in both fields, as it opens up new pathways for questions, experiments, and breakthroughs. Space exploration, too, has had a profound impact on the philosophical landscape, sparking reflections that have reshaped our understanding of existence. When humanity first ventured beyond the confines of Earth, the sheer scale and emptiness of space ignited a wave of existential thought. Questions about our place in the cosmos, our significance in the grand scheme of things, and the possibility of life beyond Earth emerged with urgency. The more we learned about the vastness of the universe, the more we began to question our own importance. One of the most famous reflections on this existential dilemma is Carl Sagan's concept of the pale blue dot. When Earth was photographed from the Voyager 1 spacecraft looking like a tiny speck in the vastness of space, Sagan's words reminded us of our fragility and our interconnectedness. The image served as a stark reminder of both our insignificance and our shared humanity. In a similar vein, the concept of cosmicism, popularized by writers like H.P. Lovecraft, explores the idea that humans are but fleeting blips in the immense, uncaring universe. These philosophical musings, rooted in space exploration, have influenced a new wave of literature and art, often exploring themes of the unknown, the incomprehensible, and the terrifyingly infinite. As humanity's journey into the stars continues, these profound reflections on our existence continue to inspire creative works that ask deep questions about the universe and our place within it. From science fiction novels to abstract visual art, the influence of space exploration on philosophy and the arts will remain a central theme for generations to come. These creative expressions challenge us to rethink our assumptions, question our beliefs, and ultimately redefine our place in the cosmos. The search for extraterrestrial life has sparked a global conversation that transcends scientific inquiry, touching deeply on the realms of ethics and philosophy. The possibility of discovering life beyond Earth, even in its simplest microbial form, poses a monumental challenge to our moral frameworks. It forces us to confront profound questions about our responsibilities to other forms of intelligent life and the ethical implications of our actions as we, as a species, venture into the cosmos. This exploration of space is not just about expanding our scientific horizons. It is about reshaping our understanding of our place in the universe and our role within it. As we probe the stars and analyze distant planets, our pursuit of knowledge has become a catalyst for philosophical reflection. It has stirred dynamic movements within the realm of ethics, causing us to rethink our duty not just to one another, but to life itself, wherever it may exist. This philosophical awakening is a direct consequence that we are no longer passive observers of the universe, but active participants. As spacefaring civilizations, we must consider the impact of our endeavors and the potential consequences of our actions on life forms, whether they are intelligent or microscopic, across the vastness of space. The quest to understand the cosmos is driven by an insatiable curiosity and wonder that reverberates through the generations. For scientists, this curiosity fuels a lifelong passion for discovery. Yet, its effects are not confined to those in the academic or scientific community. This fascination with the universe extends far beyond the lab or the observatory. It resonates with children gazing up at the night sky, filled with awe and a sense of connection to something far greater than themselves. For these young minds, the stars are not just distant points of light. They are symbols of the infinite mysteries that await discovery. When children learn about galaxies billions of light years away or the mind-boggling scale of the universe, they are not only absorbing facts, they are developing a deeper understanding of existence itself. The study of cosmic phenomena instills in them a sense of wonder that fosters their critical thinking skills and shapes the way they approach problems. As educational systems increasingly emphasize science, technology, engineering, and mathematics, STEM, the exploration of the universe becomes an essential pillar in developing the next generation of thinkers, creators, and innovators. When students engage with complex topics like the birth and death of stars or the nature of black holes, they learn how to think analytically, how to approach complex questions, and how to break down the unknown into the solvable. These lessons transcend the boundaries of space and time, shaping the very way we solve problems here on Earth. Through this educational journey, young minds are not just learning about the universe, they are being prepared to tackle the pressing issues facing humanity today. The skills developed through the study of space and science are transferable, equipping students to confront problems related to climate change, sustainable development, and technological advancement. The study of the cosmos, after all, isn't just an academic pursuit. It is a training ground for the future leaders of society, the very individuals who will find solutions to the challenges we face as a global community. Moreover, the collaborative nature of space exploration itself serves as a model for addressing the complex, interwoven problems of our world. The endeavor to understand the universe requires the coming together of diverse scientific disciplines: physics, chemistry, biology, and even philosophy. This interdisciplinary approach mirrors the teamwork and collaboration required to tackle Earth's most urgent challenges. As scientists work across these fields, they not only advance our knowledge of the universe, but also demonstrate the kind of cooperation that will be necessary to solve crises like poverty, inequality, and environmental degradation. The spirit of discovery embedded in cosmology inspires students to pursue careers that go beyond the conventional path, that contribute not just to scientific knowledge, but to societal progress as a whole. Whether they become researchers, engineers, environmental scientists, or technology developers, the lessons learned from studying the cosmos encourage them to think broadly about their contributions to humanity. They are driven not just by a desire to understand the universe, but also by the conviction that their work can improve the lives of those on Earth. At its core, the ethical dimension of space exploration is perhaps the most profound influence on young scientists. As they contemplate humanity's relationship with the cosmos, they are challenged to consider questions of sustainability, stewardship, and the long-term impact of our actions. The exploration of space compels us to think beyond ourselves, to consider our place in the grand tapestry of the universe, and to reflect on how we can act responsibly in the face of an uncertain future. Through this lens, the pursuit of cosmic knowledge is more than just a scientific endeavor. It is a call to action. It encourages a generation of thinkers who are not only committed to advancing human understanding, but also to caring for the planet we call home. As these young minds look to the stars, they are reminded that our future lies not just in the discoveries we make, but in the ethical choices we make along the way. In this way, the universe becomes more than a subject of study. It becomes a powerful motivator for shaping a better future, one that is rooted in both knowledge and responsibility.